Imagine a time before any living thing stirred on Earth. The planet is young, a newborn world, its surface unrecognizable from the tranquil blue-green sphere we know today. The ground is a vast expanse of rocky, barren land, still cooling from its fiery birth. Volcanoes punctuate the horizon, spewing glowing rivers of lava under an orange-tinted sky. There are no plants, no animals, not even the simplest microbes yet. Just a harsh, alien landscape bathed in sunlight and bombarded by meteors and relentless lightning. It is a world in flux, full of raw energy and potential, waiting for something miraculous to happen. In this primordial world, oceans are beginning to form from endless rain. Imagine warm, shallow seas pooling in craters and basins, their waters tinted a murky green-brown by dissolved minerals. The air is thick with gases we would find toxic today. Methane, ammonia, hydrogen, perhaps a touch of carbon dioxide. With each volcanic eruption and meteor impact, more chemicals mix into the waters and skies. The sun's rays and the constant lightning serve as energy, triggering countless chemical reactions in the broth of the early oceans. It's a chaotic, dynamic laboratory spanning the entire globe. In this vast cauldron of elements and energy, the ingredients for life are assembling piece by tiny piece. In these young oceans, simple molecules bump and mingle. Some bond into more complex forms, perhaps forming amino acids, the tiny building blocks of proteins. Other reactions create nucleotides, the pieces needed for the genetic scripts of life. It's a slow dance of chemistry that plays out over millions of years. To us, a million years is an unfathomable stretch of time. But in Earth's early history, such spans were the heartbeat of the planet as it gradually transformed. We can picture these ancient waters enriched with organic molecules, like a cosmic soup simmering gently, awaiting a spark. Scientists often refer to this concept as the primordial soup, a poetic image of a warm pond or quiet lagoon where life quietly begun. In one famous experiment long ago, two researchers mixed together gases believed to resemble the early atmosphere: methane, ammonia, water vapor, and then sent electric sparks. The sparks imitated ancient lightning flashing across the sky. After days of this gentle zapping, the once clear water in their flask had turned reddish-brown. Within it, they found amino acids had formed, as if by magic. This was a hint, a tantalizing clue, that under the right conditions, lifeless chemicals could self-organize into the precursors of life. It was as if nature herself had conducted the first chemistry experiment in those primordial waters, and out of that experiment emerged the alphabet of biology. Of course, forming the building blocks is only the beginning of the mystery. How did those building blocks assemble into something alive? How did simple molecules come together to form a cell capable of growing, dividing, and evolving? This is one of the universe's great enigmas. Perhaps, in some quiet corner of a tide pool, a set of molecules fortuitously arranged into a self-copying pattern, a molecule that could make rough copies of itself from the surrounding soup. It might have been something like RNA, a molecular cousin of DNA, able to both store information and catalyze reactions. Once a self-replicating molecule appeared, even imperfectly, natural selection could take hold. The copies that were a little more stable or efficient would survive longer and make more copies, gradually becoming more complex. Another idea envisions life's origin, not in a sunlit pond, but in darkness, far below the ocean's surface. Picture the deep ocean floor. No light from above, water near boiling in places as it meets molten rock beneath. Here, in these abyssal depths, hydrothermal vents spew mineral-rich water, heated by the Earth's inner fire. Around these vents, rocky chimneys form, and bizarre landscapes exist, where chemistry is driven by heat and minerals, rather than sunlight. Even in our modern oceans, scientists were astonished to discover rich communities of life clustered around such vents. Thick mats of microbes, ghostly white crabs, giant tube worms with blood-red plumes, thriving in what seems like an extreme, toxic environment. These organisms depend not on photosynthesis, but on chemical energy, using sulfur, hydrogen, and other chemicals to fuel life. This discovery showed that life could exist without sunlight, drawing energy from Earth's internal heat. If life can thrive in such places now, perhaps it could have originated there as well. The porous rocks and minerals at vent sites might have provided natural compartments, little pockets where chemicals could concentrate and react. Warm fluids cycling through these tiny chambers could create something like an incubator for life. One can imagine, billions of years ago, a vent field on the young ocean floor glowing with heat, its rocky nooks hosting a prototypical chemistry that one day crosses the threshold into the living realm. In the dark cradle of the ocean's depths, maybe life kindled like a small flame, sheltered from the chaos above. There are other intriguing clues and ideas. Some scientists think of minerals like clay as possible midwives for life. Clay particles, with their layered structures and ability to hold chemicals on their surfaces, might have helped organize organic molecules in useful ways. Picture a tidal flat, where waves periodically wash over sun-baked clay. The wetting and drying cycles could concentrate molecules, and then, as water evaporates, bring them into close contact. Perhaps in these cycles, simple membranes formed, bubbles of fat-like molecules, creating the first cell-like compartments. Within a tiny, fragile bubble, a set of reactions might be protected from the outside world, allowing complexity to blossom. And consider that Earth was not a closed box. It was part of a larger cosmos even in its youth. The early solar system was a shooting gallery of asteroids and comets. These space rocks, left over from planet formation, bombarded the young Earth frequently. While such impacts were destructive, they also could have delivered new ingredients to the surface. We know that some meteorites even today carry amino acids and other organic compounds. One famous meteorite that fell in Australia was found to contain a variety of amino acids, not from Earth, hinting that the building blocks of life are not unique to our planet at all. It's an exciting thought. Maybe some of the pieces for life were baked in space, in the icy womb of a comet, or the rocky interior of an asteroid, and then sprinkled onto the Earth like seeds falling onto fertile soil. If that's true, it opens up a tantalizing possibility. If comets and meteorites brought life's ingredients here, they could have done the same for other planets. Life's origin might not be a miraculous fluke isolated to Earth, but a natural process that could occur wherever conditions allow. Some even speculate life could have started on Mars or another world, and then travelled here on a rock knocked into space by an impact, a concept known as panspermia. In that view, we Earthlings might be descendants of Martian microbes. It's a far-fetched idea, but not outside the realm of possibility, given what we know about hardy microbes that can survive extreme conditions and the interchange of rocks between planets in the solar system. Despite all these ideas, warm ponds crackling with lightning, deep-sea vents cooking up life in the dark, clays and comets contributing their parts. The truth is, we still don't know exactly how life began on Earth. It remains one of the most profound, unanswered questions. Each hypothesis holds a piece of the puzzle, and perhaps the true origin involved elements of many of them. We have scientific evidence hinting at some pieces, ancient rocks that show chemical signatures suggestive of life as far back as 3.5 to perhaps even 4 billion years ago. Life may have begun almost as soon as our planet was stable enough to support it, which is an encouraging clue. It's as if, when conditions were right, life couldn't wait to blossom. Imagine the very first life form, likely far simpler than any cell today. It might have been just a tiny, membrane-bound sphere containing a few tangled genetic molecules and proteins, something that barely qualified as alive. It probably wouldn't survive for long by modern standards, but it wouldn't need to, so long as it could reproduce even a little before perishing. It could pass on its molecular patterns, and those patterns could improve over time, over countless generations. From these humble beginnings emerged more robust and complex cells. They learned new tricks, harnessing energy more effectively, building more complex structures, cooperating with one another. As eons passed, life on Earth evolved and diversified, from simple bacteria-like organisms to more complex cells, and eventually to the rich tapestry of life we see today. But at the heart of every living thing on Earth, from the tiniest bacterium to the tallest tree and to ourselves, lies that ancient spark that was ignited so long ago. All life shares a common ancestry. The fact that we can eat a salad or take a medicine derived from fungus or receive a heart transplant from another human shows that at a basic level, our biochemistry is the same. We are all threads in a single cloth, woven from that first living thread that appeared in Earth's deep past. It's humbling and awe-inspiring to think that every flower blooming in a meadow, every bird singing in the trees, every person dreaming under the stars is connected by an unbroken chain of life, stretching back billions of years. And at the very start of that chain is an event veiled in mystery. Perhaps it was one specific moment, a chemical reaction in a particular place and time that gave birth to the first living cell. Or perhaps life kindled in several places and only one lineage survived. We may never pinpoint the exact origin story, but we can envision it in broad strokes. A lifeless Earth gradually giving rise to entities that could take in energy, grow, and reproduce. The Earth that these first organisms inhabited was so alien compared to the one we know now. They lived in a world without oxygen in the air, for oxygen was a poison to them. The atmosphere only became oxygen-rich later, when some of those early organisms, ancestors of today's cyanobacteria, developed a way to harness sunlight and split water molecules, releasing oxygen as waste. At first, that oxygen would have been toxic to other life, causing upheaval and extinctions. But eventually, life adapted and even took advantage of this new gas. That was much later, though. In the beginning, life likely subsisted without oxygen, maybe around those hydrothermal vents or using other chemical reactions. For hundreds of millions of years, life on Earth remained microscopic and simple. Invisible mats of microbes might have carpeted shallow pools or lined the rocky cracks of deep-sea vents. These microbial colonies could have been the first ecosystems, tiny, unseen, yet busy converting energy and matter to life. Over time, some of these colonies left behind structures that have survived in the fossil record. For instance, there are ancient rock formations called stromatolites found in parts of the world. They look like layered mounds or domes of rock, but they are actually the product of communities of microbes, building up layer after layer over eons. Some stromatolites in Western Australia are nearly 3.5 billion years old. In them, we see evidence that life was already spreading and thriving in sunlit shallow waters, relatively soon after the planet had cooled enough to have oceans. Contemplating those ancient fossils, one can imagine a shallow, sunlit lagoon in the deep past, with colonies of microbe mats growing in the water, catching the sunlight and slowly laying down mineral layers. Perhaps waves gently lapped over them under a pale sky. No creature yet moved around these mats. No fish, no plants, nothing but microbes, quietly doing their work. The Earth was a microbial planet for a long, long time. Eventually, from these humble origins, life found new ways to be. Cells combined forces in symbiotic mergers. One cell swallowed another, but instead of digesting it, they formed a partnership, which gave rise to more complex cells with specialized parts. This is thought to be how the ancestors of all plants and animals got their energy factories, mitochondria, and in plants, chloroplasts for photosynthesis. Still, all this innovation traces back to that starting point, that first spark. The question of how life began is not just scientific. It touches something deeply philosophical and emotional. It speaks to our own origins. How did we go from a barren rock to a living world that eventually gave rise to thinking beings who could ask questions about their own beginnings? It's a story of transformation and emergence, and it reminds us that we are an integral part of nature, born from the same processes that shaped oceans and mountains. In a sense, we are the universe knowing itself, a collection of once lifeless atoms, now alive and pondering where we came from. While science seeks concrete answers, one can also simply marvel at the poetry of it. From lifelessness sprung life. From simplicity came complexity. From randomness came self-sustaining order. Life is the cosmos made self-aware. But in the beginning, it was just the cosmos gently experimenting with new forms. Now, billions of years after that faint first dawn of life, here we stand, breathing oxygen that early microbes released, built of complex cells that once were separate creatures, thinking thoughts and dreaming dreams made possible by neurons that evolved from those early sparks. All of it started in that deep time, under conditions so foreign to us now. Yet, the legacy of that time is within us, within every living thing. As we peer back through time with our science and imagination, trying to witness that Genesis moment, we gather clues, but the full picture remains elusive. It's as if we have pieces of an ancient puzzle, but not the complete image on the box. And so, the question, how did life begin on Earth, remains one of the great unanswered questions of the universe. We have ideas, experiments, and hints, but no definitive answer yet. The Earth holds its secrets tightly in the mists of the early Archean eon. However, this mystery, rather than discouraging us, can fill us with wonder. It reminds us that there are things we still don't understand about even our own planet's history. If life could emerge here from non-life, then the next compelling question is, could it happen elsewhere? If our once barren Earth could give rise to creatures that swim and crawl and fly, could other worlds have done the same? If life's spark ignited here, could it have ignited on the planets that share our sun, or on worlds orbiting distant stars? Our journey of curiosity thus turns outward. Having contemplated the dawn of life on Earth, we now lift our gaze to the heavens and to our neighbouring worlds. We wonder if Earth is truly unique, or if it is one of many homes for life in this vast cosmos. The story of life's origin on Earth is just one chapter of a larger story, a story that extends beyond our planet to the search for life elsewhere. With the same curiosity that drives us to explore our own beginnings, we cannot help but ask, what other lives might be out there, waiting to be found? With this question in mind, we gently set sail from the familiar shores of Earth, out into the cosmic ocean of our solar system, on a quest to find if we have company in the great darkness between the stars. Leaving Earth behind in our imagination, we venture out across the silent vacuum of space to visit our neighbouring worlds. The question guiding us is simple yet profound. If life arose on Earth, could it also exist somewhere else in our solar system? Our sun is accompanied by a family of planets and moons, each unique. Perhaps one or more of these siblings of Earth has managed to spark its own biology. As we drift outward from the blue marble of Earth, the first destination that captures our curiosity is our red neighbour, Mars. Mars, cold and quiet now, was not always the frozen desert we see today. In the distant past, Mars was a world of flowing water. Imagine standing on ancient Mars, billions of years ago, a pinkish sky above, and on the ground, a river rushing past, fed by melting snow on distant hills, lakes pooled in craters, and perhaps a vast northern ocean stretched towards the horizon. Mars was warmer then, its surface protected by a thicker atmosphere. For perhaps hundreds of millions of years, liquid water, a key ingredient for life as we know it, was abundant on Mars. If you could travel back in time, you might see Martian landscapes that in some ways resembled young Earth. Volcanoes, valleys carved by rivers, deltas where streams spilled into lakes, carrying sediments rich in minerals. It isn't hard to imagine that in those wet epochs, tiny Martian microbes might have swum in the muddy waters or clung to rocks by the shore. Today, Mars is stark. Over eons, it lost most of its atmosphere, and with it went the surface water. What remains are ghostly riverbeds etched in the rocks, dry lake bottoms, and mineral deposits that tell a story of a wetter past. The planet's once active volcanoes are silent giants looming over a barren landscape. Yet even in this inhospitable present, Mars still teases us with hints that it might not be entirely dead. For instance, scientists have detected a mysterious trace of methane gas in the Martian air, which appears and disappears seasonally. Methane can be produced by geological processes, but on Earth, a lot of methane comes from living organisms. Could it be that something underground on Mars is breathing out this gas even now? We don't know for sure, but the possibility keeps our hope alive that Mars might harbour life in some hidden niche. On Mars, the search for life is a careful, patient endeavour. We have sent our mechanical envoys, rovers the size of cars that trundle across the Martian surface, inspecting rocks and soil. These robotic explorers, with their delicate instruments, have found organic molecules in Martian soil and drilled into rocks that likely formed in ancient lake beds. One rover is quietly caching samples, sealing bits of Martian rock in small tubes, intending for a future mission to bring them back to Earth someday. When those samples arrive, scientists will scrutinize them for patterns or substances that might indicate past life. Perhaps within a shard of mudstone from an old lake bed, there could lie the fossilized imprint of a microbe that lived billions of years ago when Mars was blue and alive. As we drift alongside our rover companions in spirit, imagining the barren plains around us, it's striking how lonely Mars feels. But our journey doesn't end here. Mars is just one world. There are other intriguing places orbiting our same sun that could nurture life, even if they seem unlikely at first glance. We venture further out, leaving the inner solar system behind. Beyond Mars lies the asteroid belt, a swarm of rocky debris, and then the realm of the gas giant planets. These huge planets themselves are mostly atmosphere and crushing pressure deeper down, not hospitable for life as we know it. But circling those giants are moons that have become prime targets in our search for life. One of the most beckoning of these moons is Europa, which belongs to mighty Jupiter. At first glance, Europa might not seem promising. It's a bit smaller than our own moon and covered in ice. Yet, that very ice is the key to its allure. Europa's surface is a shell of water ice, bright and streaked with mysterious cracks and ridges. The patterns on the ice tell a story. They suggest that beneath the solid crust lies a deep global ocean of liquid water. How can there be liquid water so far from the sun, where sunlight is weak and the temperatures far below freezing? The answer lies in Europa's heart. Jupiter's gravity tugs and squeezes Europa as it orbits, a process called tidal heating. This flexing generates heat inside Europa, enough to keep an ocean liquid under the frozen surface. So, while Europa's exterior is a frozen wasteland, perhaps 15 or 20 miles thick, beneath that icy crust could be an ocean 40 or 50 miles deep, containing more water than all of Earth's oceans combined. Now, imagine that hidden European ocean. In the pitch black, far beneath the ice, the water might be gently warmed by heat from the moon's core or seafloor, maybe hydrothermal vents, similar to those on Earth's ocean bottom, dot Europa's seafloor, releasing mineral-rich, warm fluids into the cold seawater. If so, they could create an environment where life might gain a foothold. On Earth, places like this teem with microbes and exotic creatures, even without sunlight. Could Europa be the abode of extraterrestrial life, living in eternal night under the ice? Perhaps simple organisms like bacteria or something akin to tube worms clustered around warm vents, or maybe just microscopic plankton drifting in the dark sea. We don't know if anything lives there, but Europa provides a tantalizing combination of ingredients: water, energy, and a suite of chemicals. Everything life as we know it requires. Scientists and engineers are so excited by Europa that they are planning missions to take a closer look. One upcoming spacecraft will orbit Jupiter and swoop by Europa repeatedly, scanning the ice with radar to map the ocean beneath, tasting the trace chemicals in Europa's whisper-thin atmosphere, and searching for any hints of organic molecules. We yearn to someday drill through that ice, or send a submarine to plunge into Europa's ocean, to finally see what might be swimming, or floating, or just metabolizing quietly in those alien depths. For now, as we hover in our imagination above Europa's cracked ice plains, we feel the profound silence of a world encased in ice. All is still on the surface. No sound, no movement. Yet below, if we listen with our mind's ear, we might almost sense the faintest ripple of something stirring in the dark waters. Our next destination lies even farther, orbiting the ringed jewel of Saturn. Saturn, like Jupiter, is a huge gas giant with a family of moons. One moon has captured our attention in the quest for life, the tiny, bright Enceladus. Enceladus is an icy moon, much smaller than Europa, only about 300 miles across. You could fit Enceladus within the length of Great Britain. It shines brightly because its surface is also covered in fresh, clean ice. But Enceladus is not a dormant ball of ice. It's surprisingly active. As we approach Enceladus, we see something breathtaking. Enormous geysers erupting from cracks near its south pole, spraying water vapor and ice particles out into space. These plumes are like giant fountains, and they tell us that Enceladus, like Europa, harbors liquid water beneath its surface. In fact, those geysers allowed scientists to sample Enceladus's hidden ocean without ever landing on the moon. A spacecraft named Cassini, which toured the Saturn system for many years, flew through the plumes and analyzed what they were made of. It found water, as expected, but also a variety of organic molecules, carbon-based compounds that are the fingerprints of chemistry, interesting to life. Even tiny grains of sand-like particles, thought to come from hydrothermal vents on Enceladus's seafloor, were detected. Intriguingly, the plumes also contained simple molecules like hydrogen gas, which on Earth, around hydrothermal vents, serves as food for some microbes. The discovery of hydrogen indicated that there are likely chemical reactions between water and rock happening at Enceladus's ocean floor, perhaps similar to the processes in Earth's oceans that support life in the deep. All of this adds up to a compelling picture. Enceladus, despite its diminutive size, has a global ocean under its ice, likely heated by hydrothermal vents, loaded with organic compounds and potential energy sources for life. If one had to draw up a checklist for a habitable environment, Enceladus seems to meet many criteria. The main question is, did life ever get started there? If it did, might it still be living in that ocean, multiplying slowly in the cold dark, perhaps gathering around warm vent chimneys, just as life does in Earth's oceans? One can picture it in the mind's eye. Black smoke vents on Enceladus's seabed, hot fluids gushing out, and around them, invisible microbial communities feeding on the chemistry, completely oblivious to the icy crust and the Saturnian rings overhead in the vacuum of space. From Enceladus, we travel to another Saturnian moon that is a world of wonders, Titan. Titan stands out because it is unlike any other moon, indeed, unlike any other place in the solar system, including planets. In one fascinating respect, Titan has a thick atmosphere and is the only other body in our solar system with stable liquid on its surface, though not liquid water. As we descend through Titan's smoggy golden atmosphere, we find ourselves in a bizarre but strangely Earth-like landscape. The air is dense and cold, mostly nitrogen like Earth's atmosphere, but with a dash of methane. The ground below reveals lakes and rivers, but they are filled with liquid methane and ethane, hydrocarbons that are gases on Earth, but liquid in Titan's frigid climate. It's as if we found an alien version of Earth, where water is replaced by liquid gas. On Titan, the temperatures are around 180 degrees Celsius, far too cold for liquid water on the surface. Any water there is hard as rock. Instead, methane and ethane take on the role of water, cycling through Titan's environment, evaporating from lakes, forming clouds, falling as rain, carving channels in the ice crust. It's a complete hydrological cycle, just with different materials. At such cold temperatures, life as we know it, which relies on liquid water for chemistry, would have a very hard time. However, Titan is rich in organic molecules. In fact, its sky is filled with a haze of complex carbon-rich chemicals that settle on the surface. Some scientists speculate that if any life exists on Titan, it would have to be very different from life here, perhaps using liquid methane as a solvent instead of water, and with chemistry we can barely imagine. It would be a form of life truly alien to us. Titan also has another secret. Beneath its icy crust, like Europa and Enceladus, Titan is believed to have a hidden subsurface ocean of liquid water mixed with ammonia. So Titan could offer two very different habitats. A surface where any life would be exotic and methane-based, and a deep subsurface ocean where more familiar water-based life might possibly exist. It's a long shot, but Titan intrigues us because it shows how diverse conditions can be on other worlds, and it reminds us not to be too narrow-minded in our thinking of life's possibilities. After all, life on Earth has surprised us by adapting to some extreme niches. Microbes that can survive in acid hot springs, in radioactive waste, in the freezing dry valleys of Antarctica, and even inside rocks deep beneath the sea floor. Life, if given the chance, can be remarkably resourceful and tenacious. And what about our other neighbouring planet, Venus? Now here is a world that, at first glance, looks utterly hostile to life. Venus is a hellish place now. Its surface is as hot as an oven set to broil, hot enough to melt lead. And its atmosphere is a dense, stifling blanket of carbon dioxide with clouds of corrosive sulfuric acid. No water flows there now. Any oceans it once had have long since boiled away. But scientists suspect that Venus wasn't always so infernal. Once, billions of years ago, Venus might have been more temperate and wet, perhaps Earth's twin in more than just size. It may have had shallow seas and mild weather for a time, before a runaway greenhouse effect turned it into the choking oven it is today. If so, life could have had an opportunity to begin on Venus in that bygone era. Any Venusian microbes would have either perished or retreated into niches as conditions worsened, and it's hard to imagine anything surviving on the surface now. Yet, interestingly, some scientists have proposed that life on Venus might persist not on the ground, but high up in the atmosphere. About 30 to 40 miles above Venus's surface, the temperature and pressure become surprisingly Earth-like, though the environment is still extremely acidic. In this zone of Venus's atmosphere, there are thick clouds. In 2020, a group of researchers reported detecting a gas called phosphine in those clouds, a gas that, on Earth, is associated with microbial life. The finding was controversial and is still debated, but it raised the question, could there be cloud-borne microorganisms in Venus's atmosphere, floating in droplets of sulfuric acid, eking out a living in the only habitable niche left on a ruined planet? It's a haunting idea. Life in the skies of Venus, drifting endlessly, perhaps dormant most of the time, waiting for fleeting moments when conditions in a droplet are just right. We have no proof this is happening, but Venus has reminded us that even the most unwelcoming world could hold surprises. Beyond Mars, Europa, Enceladus, Titan, and Venus, there are other places in our solar system one might wonder about. Jupiter's moon Ganymede, for instance, and Neptune's moon Triton are thought to have subsurface oceans. Even Pluto, in the far reaches of the solar system, beneath its ice, might have a layer of slushy water. These are mostly speculative as far as life is concerned, but they underscore a key point: the traditional notion that only planets in the habitable zone, the right distance from a star for liquid water, can have environments for life, has expanded. Moons around giant planets can have oceans by internal heating. Planets that might be too cold at the surface can have warm niches underground. So when we search for life, we cast a wide net. For now, our only data point is Earth. As far as we currently know, Earth is the only place that actually harbours life. Every other world we've explored, whether with telescopes or robotic probes, has yet to yield solid evidence of even a single microbe. But we have to remember, we've only begun to scratch the surface. Literally, in the case of places like Mars, we've dug just a few inches into the ground. We have not yet brought back samples from Mars's ancient rocks to scrutinize in our best labs. We have not yet cracked through the ice of Europa or Enceladus to see what lies beneath. We have not sniffed definitively at Venus's clouds with life detection instruments, though there are proposals to do just that. It's as if we've peeked through a keyhole of a great mansion when it comes to exploring for life. There is so much more we need to observe and discover. Consider how vast and varied the environments on Earth are, and how life has managed to infiltrate nearly every niche. Microbes have been found alive in the deepest parts of the ocean, where pressures are immense and sunlight absent. Bacteria have been discovered in South African gold mines, living in water-filled cracks miles underground, isolated from the surface for eons, nourished by the chemical reactions between rock and water. Tiny organisms flourish in the super salty, toxic waters of the Dead Sea and in the scalding hot springs of Yellowstone. and high in our own atmosphere, miles above the ground, scientists have captured microbes that float in the sky. Life is crafty and resilient, at least here. So, when we think of Mars or Europa or others, we try to remember that even if conditions seem extreme, our baseline for too extreme has changed. What once seemed uninhabitable might be habitable to something microscopic and unassuming. The search for life in our solar system has become one of the driving goals of modern space exploration. In the next decade or two, new missions will carry sophisticated instruments to these intriguing places. They will drill, scoop, listen, and analyze, seeking the faint chemical whispers that biology might leave behind. Perhaps it will be a particular mix of gases in the Martian atmosphere that finally betrays the presence of microbes below, or a complex organic molecule in the plumes of Enceladus that is hard to explain without life, or maybe even direct imagery under a microscope from a sample returned from Mars, or dug up on the moon someday. For who knows, perhaps ancient life from early Mars could have hitchhiked to the moon on ejector long ago, leaving fossils in lunar soil. These missions reflect our deep longing to know whether we are alone in our neighborhood. Imagine the day when a definitive sign of life beyond Earth is found, a microscopic fossil in a Martian rock, or a peculiar molecule in an alien ocean that can only come from metabolism. Such a discovery would be profound. It would tell us that life is not exclusive to Earth, that the spark that lit in our primordial seas was not a one-off event. It might mean that the universe is teeming with life, that wherever there are Earth-like conditions, life will sprout, given enough time. Even if we find only microbes, it opens the door. Given billions of years, might those microbes evolve into complex life and maybe intelligence? Or if life started on Mars and Earth independently, perhaps it was common in the solar system, suggesting it might be common in the galaxy. As we reflect on these possibilities, a gentle sense of connection comes to mind. We on Earth have always been living in the midst of a cosmic archipelago, each planet and moon a potential island of life. So far, we've only confirmed life on one island, but just knowing others could be inhabited changes how we see the night sky. The moon becomes not just a dead rock, but perhaps a vault that might contain ancient spores or clues from Earth or Mars exchange. Mars becomes a potential stop on the tree of life, either a sibling of Earth's life or an independent experiment. The icy moons become enormous oceanic habitats waiting to be explored. The solar system, though mostly forbidding, starts to feel a bit more like home when we imagine life might be scattered here and there in its corners. Now let's take stock. We've journeyed from Earth to the far reaches of our solar system in pursuit of life's footprints. We haven't found clear footprints yet, but the sands of Mars, the waters of Europa and Enceladus, the clouds of Venus and the lakes of Titan all beckon with possibilities. These are places accessible to us with our current or near future technology. They are within reach of our probes, and one day, perhaps within reach of human explorers. The question, could there be life in our solar system, remains unanswered for now. But we are steadily learning more, and perhaps on the brink of discovery, just as the first chapter of life's story on Earth is being slowly deciphered. The potential second chapter, life starting anew on another world, lies open and waiting for us to read. Our journey doesn't end at the edge of the solar system. Beyond the orbit of Neptune, beyond Pluto's distant icy plains, the sun's influence wanes and interstellar space begins. But out there, scattered in the galaxy, are billions upon billions of other suns, each a star that could host its own family of planets. As we exhaust our immediate neighborhood's wonders and questions, our gaze inevitably turns to these distant suns. If life might exist on a few of our local worlds, how many more might there be among the stars? Could there be another planet out there, far beyond our sun's reach, that has oceans and continents and life forms, gazing back at the cosmos as we do? It's time to leave the familiarity of our solar system entirely and voyage into the wider galaxy where countless other worlds beckon, a journey to find other Earths in the cosmos, and perhaps other beings who call those Earths home. The stars in the night sky have always inspired wonder. For most of human history, they were thought to be distant, unreachable suns, perhaps with their own worlds, but we had no proof. People could only speculate about whether other Earths circled those points of light. In the last few decades, this speculation has transformed into discovery. Now we know that planets are abundant in the galaxy. In fact, almost every star you see likely has at least one planet, and often many. The cosmos, it turns out, is filled with worlds. Imagine drifting through space toward a nearby star. As you approach, you notice a faint speck of a planet crossing in front of the star's bright face. From afar, all you might see is a tiny silhouette, but that small shadow is a world unto itself. In recent years, astronomers have become adept at noticing these faint shadows. By watching the light of stars very carefully, they can detect the slight dimming that happens when a planet passes in front of its star, an event called a transit. Each transit is like the ticking of a clock, telling us about a planet's orbit. With such methods, and others like measuring a star's slight wobble due to a planet's gravitational tug, thousands of planets outside our solar system, exoplanets, have been found. These range from gigantic planets larger than Jupiter to small rocky ones only a bit bigger than Earth. What we're most interested in, for the question of life, are planets that resemble our own Earth in some key ways. They should be rocky, roughly Earth-sized, and at the right distance from their star for liquid water to exist on their surface. This right distance is often called the habitable zone, or the Goldilocks zone. Not too hot, not too cold. If a planet is too close to its star, it will be scorched, like Mercury or Venus. And if it's too far, it will be frozen, like Mars can be, or the outer planets. But in that middle band, water could remain liquid, rains could fall, rivers flow, conditions that, at least on Earth, nurtured life. It turns out such planets are not just science fiction. We have already found a number of candidates. Some orbit stars similar to our Sun, others circle dimmer, smaller stars called red dwarfs. One of the first Earth-sized planets discovered in a star's habitable zone is named Kepler 186f. It's an intriguing world, roughly the size of Earth, orbiting a cool red dwarf star about 500 light-years away. On its star's surface, the light might be a bit more reddish than our sunlight, but if Kepler 186f has an atmosphere and water, it could potentially have a temperate climate. We don't know for sure. It's so far that we only know it as a faint signal in the data. But just knowing it exists is thrilling. It's like knowing a book exists without having read it. We can only imagine its content. We imagine perhaps a planet with ruddy-hued skies and exotic plants, if any exist, adapted to the red glow. A serene world, circling quietly in the darkness, unknown to us, except as a tiny dip in starlight. And there are closer candidates. In 2016, astronomers announced the discovery of a planet around the very closest star to our solar system, Proxima Centauri. This star is a small red dwarf, and the planet, called Proxima b, is about the mass of Earth and lies in that star's habitable zone. Proxima Centauri is just over 4 light-years away, extremely far for us, tens of trillions of miles, but a next-door neighbour in galactic terms. If we could somehow travel at the speed of current spacecraft, it would still take tens of thousands of years to get there. But in our minds, we can make the journey in an instant. Picture Proxima, because its star is a red dwarf and much dimmer than the Sun. The planet orbits very close to its star to get similar warmth, much closer than Mercury is to our Sun. It might even be tidally locked, where one side always faces the star, the other in eternal night, presenting a permanent day side and night side. If there's life there, it could be very different, enduring fierce stellar flares from its active sun. Yet, Proxima b remains one of the tantalizing nearby targets in the search for another Earth, precisely because it is so close and potentially rocky and temperate. Then there is the remarkable system of TRAPPIST-1, a star not much bigger than Jupiter, with a whole family of 7 known planets, all of Earth-like size. This amazing discovery, announced in 2017, revealed that at least 3 of those planets orbit in the star's habitable zone. Imagine a sky where, if you stood on one TRAPPIST-1 planet, you might see several of your sister planets as sizable crescents or disks hanging in the sky, some larger than our moon appears to us. They would be close enough to each other that travel between them would be easier than travel between planets in our solar system. Each of these 7 siblings could have its own character, one perhaps covered in ice, another maybe with an atmosphere thick and steamy, others possibly with oceans. We don't know their actual conditions yet, but scientists are eagerly studying them for clues. Because TRAPPIST-1 is relatively nearby, about 40 light-years away, We can train our new telescopes on it. The James Webb Space Telescope has begun observing some of these planets, trying to detect if they have atmospheres and what those atmospheres contain. The hope is to find indicators that a planet might be Earth-like, perhaps even signs of water or certain gases that on Earth are tied to life. What would a sign of life look like from so far away? We can't see these exoplanets directly in detail. They're too tiny and distant. But we can analyze the starlight that filters through their atmospheres when they pass in front of their star. If that starlight carries the fingerprint of certain molecules, we might infer what the air there is like. On Earth, for example, our atmosphere is unusual because it has a lot of oxygen, a very reactive gas, coexisting with methane. Oxygen, as abundant as it is in our air, wouldn't last long, in geological terms, if not continually produced by life. Plants, algae, and bacteria produce oxygen through photosynthesis. So, if astronomers find an exoplanet with a similar imbalance of gases, like oxygen alongside methane or other combinations that are hard to sustain without life, it would be a strong clue that something biological is active there.
This search for biosignatures, life signs, in exoplanet atmospheres is just beginning. We haven't yet spotted a clear, "Hey, there's life," signal, but the fact that we have the tools to look is in itself astonishing. The James Webb Telescope has the sensitivity to detect some of these gases on planets around the nearest stars. If conditions are right, in the coming years, perhaps we will find a whisper in the data that makes scientists sit up and double-check. An unexpected blend of gases, or maybe even something like chlorophyll's spectral signal, a pigment plants use, which could tint a planet's reflection in a detectable way. Future missions, even farther down the line, might attempt to take pictures of Earth-like planets by using special techniques to block the star's light, a star shade or advanced coronagraph, to see the faint planet next to it. Those images, if we ever get them, won't be detailed like a NASA photo of Earth. They'd likely be just a speck or maybe a single pixel of light. Yet in that single pixel, we could analyze color and light to guess whether it's a blue ocean planet, a green forested one, or a barren rock.
Let's consider how many potential Earths might be out there. Our Milky Way galaxy contains roughly a few 100 billion stars. Even if only a small fraction of those stars have Earth-sized planets in the habitable zone, that could still be millions or even billions of worlds. One analysis of Kepler Space Telescope data, Kepler was a pioneering planet-hunting mission, suggested there could be as many as 300 million potentially habitable planets in our galaxy alone. And remember, there are hundreds of billions of galaxies beyond our own. The sheer numbers become mind-boggling. Of course, potentially habitable just means the conditions might be right. Not that they definitely have life. But with so many chances, it feels hard to imagine that Earth is the only one where the chemistry of life has taken root. The idea of other Earths has long appeared in our stories and dreams. We have imagined alien worlds in countless books and movies, some with lush jungles, others with twin suns, or rings arching across the sky. As science has progressed, we've begun to realize that reality might not be so far off from imagination. We've found planets that have some similarities to the fictional ones. Planets with two suns. Circumbinary planets have been discovered, indeed like Luke Skywalker's Tatooine in Star Wars. One called Kepler 16b is an example of a world with a double sunset. Planets that are predominantly ocean, so-called water worlds, are hypothesized, and some exoplanets found have densities that suggest they are mostly water or ice. There are planets bigger than Jupiter, in scorching hot orbits, so close to their star that a year lasts mere days. The hot Jupiters, which once were beyond our wildest speculation, but turned out to be relatively common in our surveys. This diversity has opened our eyes. Our solar system, with its neat arrangement and life on one planet, might not be the only template. There might be solar systems where two neighbouring planets both harbour life, or systems where life leaps from one moon to another. When we say other Earths, we are looking for planets that could be enough like Earth to support life, but they will not be identical twins. Each planet is a product of its own star and formation history. Some might be slightly bigger, which could mean thicker atmospheres and perhaps even more stable climates. Some might be a bit smaller, or have more water, or orbit a star that is redder or bluer than our Sun. Each difference might influence what kind of life, if any, develops. On some worlds, maybe life never makes it past microbes. On others, if the conditions are right and time is plenty, perhaps something with intelligence and culture evolves, as it did here. One cannot help but wonder what the night sky looks like from one of those distant inhabited planets, if they exist. Do they see our Sun as a tiny star? Possibly. If they had their own astronomers, have they noticed Earth as a faint shadow crossing the Sun? And if so, have they realized that our atmosphere has oxygen and water? In essence, are they searching for us as we search for them? Such thoughts have a way of making the universe feel both vast and intimate at the same time. Vast, because the distances are enormous and the numbers of stars staggering. Intimate, because it suggests a kinship with unknown life forms that might be out there, a sense that we all share the same broader universe. The atoms in our bodies were forged in stars. In that way, we are already connected to the cosmos. But the possibility of living counterparts out there, even just simple bacteria on an exoplanet, adds another layer to that connection. To detect an exoplanet and learn about it is a bit like hearing a few notes of music from an unseen source. We might catch the faint strain of a melody, but not know the full song. We interpret those notes, the data, the spectra, to guess at what instruments are playing, the planet's conditions. Is it a lullaby of a calm, life-friendly world, or a discordant cacophony of a barren one? Each discovery is an invitation to imagine. So far, the exoplanets we've found have surprised us again and again. For example, there's a planet called K2-18b, about 124 light-years away, which is in its star's habitable zone and is bigger than Earth, a mini Neptune size. Astronomers looked at its atmosphere and found signs of water vapour, and possibly even hints of other molecules that could be associated with life. Although it's more like a scaled-down Neptune, with maybe a deep ocean under a hydrogen-rich sky. It's not an Earth twin, but it raises interesting possibilities about different types of habitable environments. Also, some planets that are in the habitable zone might not actually be habitable, and vice versa. Venus and Mars could be considered within or near the Sun's habitable zone. Venus is clearly not habitable now, and Mars is right on the edge. Meanwhile, moons like Europa and Enceladus are outside the traditional habitable zone, but have internal water and heat. So when looking at exoplanets, scientists also consider many factors. Does the planet have a thick atmosphere to keep water from freezing if it's a bit far out? Does it have any protective magnetic field to shield life from cosmic radiation? Is the star stable, or does it blast the planet with flares? There are so many variables, and we have limited information on each discovered world.
Nevertheless, the quest to find another Earth, especially one that might already have life, is like a grand detective story. We gather clues, a dimming of starlight here, a spectral line there. We piece together a picture, perhaps a planet with moderate temperatures and an atmosphere with water clouds, maybe a hint of oxygen. Then we have to ask, what could cause that oxygen? If not life, is there a geological explanation? And if life, what kind? It's an exercise in both science and imagination.
This search is also the prelude to something even more audacious. Not just finding another Earth, but potentially communicating with whatever inhabitants it might have, if they are advanced. That crosses into the next part of our cosmic questions. If such life exists, especially intelligent life, why haven't we heard from it? But before we jump ahead, we pause and marvel at what we have achieved so far. From a situation not long ago, where we only knew of the planets circling our sun, we now know of thousands of exoplanets, including many small, rocky ones. We're finding that the ingredients for habitability, water, the right temperatures, and the right chemical elements are not rare in the cosmos. Even the stuff of life, the molecules like amino acids and sugars, have been detected in space, in meteorites and in gas clouds. The universe seems to be primed for life, scattering the raw materials everywhere. So the existence of other Earth-like worlds gives us a stage on which this cosmic chemistry could play out similarly to how it did here. We should also remember that life could be a broad term. Even if we find that a planet has, say, simple algae or bacterial life, that would be a monumental discovery. It could also be that life elsewhere might not be identical to ours. Perhaps it uses different biochemistry. But planets like our Earth, with liquid water and a stable climate, give us a good starting assumption that any life there might at least rhyme with life here. As we reach out with our instruments and our minds to these other worlds, we feel a sense of anticipation. Imagine the moment when we identify a planet truly similar to Earth in size, composition, and temperature. And then we detect oxygen in its atmosphere, perhaps even seasonal changes in that atmosphere that could hint at plant life or something analogous. It would arguably be one of the most significant discoveries in human history, the confirmation that life has taken hold elsewhere. For now, we are like sailors on a shore, looking out at a vast ocean of stars, with hints of lands, planets, across the water. We have maps drawn by our telescopes, indicating where some of these lands are, how far, and of what size. We can even glimpse a little of their climate from those maps. But we haven't yet set foot, not even robot foot, on any of them. They are far beyond reach with current technology. Our contact is all indirect. Still, that hasn't stopped us from learning a surprising amount. With each new discovery of an exoplanet, we refine our understanding of how planetary systems form and how unique or common Earth might be. So, are there other Earths in the cosmos? Almost certainly there are other planets very much like Earth, in terms of size and potential habitability. Whether they are truly Earth-like in having life or civilizations is the grand question still before us. The probability seems in favor of at least some, and if there are many, it raises another question that has puzzled scientists and thinkers for decades. If there are other Earths, and presumably other forms of life, maybe even intelligent life, then where are they? Why haven't we seen obvious evidence of alien civilizations? It's a question we carry with us as we conclude our contemplation of distant worlds and turn to face the silent stars with a new question on our lips. Where are all the aliens? The question now hanging in the air is one that has haunted scientists, philosophers, and anyone who has looked up at the stars. If the ingredients and opportunities for life are so abundant, and if the cosmos might be teeming with living worlds, then where is everyone? Where are the aliens, the other intelligences, the voices from the stars? It's a question famously posed by the physicist Enrico Fermi in the 20th century during a casual lunch conversation, and it remains poignant today. The night sky above us is vast and filled with billions of stars. By all logic, some of those stars should host planets with life, perhaps even intelligent life that can build technology. And if even a few of those civilizations advanced enough and endured long enough, wouldn't they have reached out, or travelled, or at least left some sign? Yet, as far as we can tell, we hear nothing but a great silence. This conundrum is often referred to as the Fermi paradox, the apparent contradiction between the high probability of extraterrestrial civilizations and the lack of evidence for, or contact with, such civilizations. Put simply, given the immense number of stars and the timescales involved, one might expect that the universe, or at least our galaxy, would be buzzing with life and signals, but we haven't detected any clear messages or seen any unmistakable visitors. Is it possible we are, if not completely alone, at least very isolated? There are many ideas about how to resolve this paradox, and each idea offers a different perspective on our own place in the universe. One possibility is that life, and especially intelligent life, is simply very rare. Maybe the conditions that led to life on Earth are exceedingly uncommon. Perhaps lots of planets have microbes, but getting from single-celled life to complex creatures is not guaranteed. After all, for a huge stretch of Earth's history, roughly 3 billion years, life remained at the microscopic stage. It took a series of unlikely events to produce larger organisms and eventually animals. Maybe on most planets, life never evolves beyond slime in a crater or microbes in an ocean. Even if complex life does arise, the path to intelligence and civilization might be precarious. The dinosaurs were the dominant animals on Earth for over 150 million years, yet they did not build radios or rockets. An asteroid sealed their fate. But if not for that random event, perhaps mammals, and eventually humans, might never have gotten their chance. We, humans, have only been around for a few million years, and our technological civilization, able to communicate over interstellar distances with radio, has existed for barely a century. That is a tiny blink of an eye on cosmic scales. Other civilizations might be equally fleeting. Perhaps intelligent life arises somewhere, flourishes briefly, and then either fades away or destroys itself. This brings up a darker resolution to the Fermi paradox. Maybe intelligent civilizations don't last long. It's a sobering thought. A civilization might invent powerful technologies, but those might inevitably lead to crises. Nuclear war, catastrophic climate change, or other self-inflicted catastrophes that cause it to collapse. Or maybe they exhaust their planet's resources or face other cosmic threats, like supernovae or massive asteroid impacts, before they manage to spread out to the stars. If the lifetime of technologically active civilizations is short, it could explain why we don't overlap with others in time. They may flicker in and out across the galaxy, like fireflies in a vast forest, rarely if ever seeing one another. Another angle is distance and time. The galaxy is immense, about 100,000 light-years across. If a civilization is, say, 50,000 light-years away, their signals, travelling at the speed of light, would take 50,000 years to reach us. Human civilization, in its current form, wouldn't have been around to pick up a signal that left their planet during the last ice age. And who knows if we'll be around 50,000 years from now to receive one sent today. In other words, even if others are out there and sending out signals, the timing might not line up with our brief window of listening. We've only had radio telescopes for a handful of decades. If an alien society beamed a message toward Earth in the year 1000 BCE, we wouldn't have heard it. And if they gave up after not hearing back, that opportunity would have been missed. There is also the challenge of technology and detection. We assume aliens might use radio waves or lasers to communicate, because that's what we are familiar with. But what if they use something else entirely? Something we haven't discovered or thought of? Communication might be happening all around us, in a form we don't recognize. Or maybe they communicate in ways that are very slow or subtle. Or they focus communication inward, like using tight beams or networks among their own colonies, and aren't broadcasting to the universe. The notion of broadcasting is itself worth pondering. Earth has been unintentionally broadcasting radio and TV for about a century, and intentionally sent a few messages, like the Arecibo message in 1974, which is a bit of binary code aimed at a star cluster. But those signals weaken as they spread out. By now, our earliest broadcasts have washed over many nearby stars, but to detect them at those distances would require huge antennas, and perhaps they would be indistinguishable from background noise. So, even if someone around another star is listening, they might not easily detect our presence yet. Similarly, we could be missing their faint whispers. It's possible that advanced civilizations have moved beyond broadcasting loudly. Perhaps they learned it's wise not to shout into the cosmos. There might be unknown dangers, or they simply have no interest in calling out to random stars. Some thinkers have posed what's called the zoo hypothesis, the idea that advanced aliens know about us, but choose not to interfere or contact, letting us develop naturally, much as zookeepers don't usually jump into the animal enclosure and try to converse with the creatures. If that's the case, then the silence is intentional on their part. We are effectively being ignored or observed passively. And then there is a whimsical but haunting idea that maybe we truly are the first, or at least among the first, intelligent civilizations to emerge in our galaxy. Someone has to be first. If out of the billions of years of cosmic history, the moment for civilizations is only beginning, we might be at the forefront. If that's true, the responsibility on our shoulders is enormous. We would be the trailblazers of conscious life in the galaxy. It also means the loneliness is real, but perhaps temporary if others come after us. On the other hand, perhaps civilizations are common, but they are all, by cosmic coincidence, so far apart in space and time that they effectively never meet. Our galaxy could host, say, 100 civilizations spread out over millions of stars and millions of years. The vast distances mean each one is an island, a solitary beacon that might never overlap with another. One civilization might rise and fall in one corner, unaware that a few others exist, scattered in distant sectors, separated by such gulfs that contact is impractical. Of course, it's also possible that there are signs of aliens that we have seen but not recognized. Some have speculated that unusual astrophysical phenomena, like certain repeating radio bursts or the peculiar dimming of a star. Famously, a star called Tabby's star showed weird brightness dips that some thought could be due to a megastructure built by aliens, though natural explanations like dust are more likely, might be evidence of advanced engineering. So far, nothing has been confirmed to be artificial in origin, but the mere fact we're considering such possibilities shows how eager and open-minded we are becoming, trying not to miss anything. We have active searches dedicated to finding a signal. The Search for Extraterrestrial Intelligence, or SETI, has listening posts that scan the heavens for anything that stands out as non-natural. They sift through billions of radio channels, looking for a steady beep or an ordered sequence of pulses that nature alone wouldn't produce. At times, they've gotten brief hits, like the famous WOW signal detected in 1977, a strong, unexpected signal that lasted about a minute and then never repeated. To this day, it's unexplained, but because it never came back, it remains a curiosity rather than proof. SETI efforts continue, growing more sophisticated, now using multiple telescopes and even harnessing the power of distributed computing. Volunteers around the world have aided by letting their computers analyze data, as in the SETI at Home project. But the haystack is enormous, and we've only examined a tiny fragment of it. We've mainly listened for radio waves around certain frequencies, for stars relatively nearby. The vast majority of the sky and many wavelengths remain to be searched.
There are also new ideas, looking for techno-signatures beyond just radio. For instance, if a civilization built structures on a colossal scale, like city lights covering a planet, or a swarm of satellites around a star, we might detect unusual infrared emissions or odd, dimming patterns of starlight. If a civilization heavily polluted its atmosphere, some irony here, we might detect the spectral signature of those pollutants on an exoplanet. These are speculative, but they broaden the ways we might stumble upon evidence of someone out there.
Now imagine for a moment that tomorrow we detected something undeniable. A complex, repeating signal coming from a star system 100 light years away. Suppose it clearly encoded patterns that could not be natural, perhaps pulses that count out prime numbers, or some mathematical sequence. The realization would dawn. We are not alone. There is another intelligence. How would that feel? It might be both exhilarating and frightening. Exhilarating to know that life and mind have arisen elsewhere, that the questions we have asked, we could perhaps ask together. Frightening because it challenges our place in the universe and raises new uncertainties. Who are they? What are their intentions? How advanced are they?
Now imagine the opposite scenario, that we continue listening for centuries and find nothing, or we find only simple life in our solar system, and some fossil bacteria on Mars, and evidence of algae on an exoplanet, but no one else to talk to. How would that feel? There might be a certain melancholy in thinking we are the only ones who built cities and radios and wondered about the universe. On the flip side, it would also mean the cosmos is an open frontier with no competition, and we truly carry the mantle of intelligence for now. Between these extremes lies a quiet persistence. Keep searching, but also keep reflecting on what it means either way. In a sense, the search for aliens is also a way of holding a mirror up to ourselves. When we ask, "Where are the aliens?" we also implicitly ask, "What are we, and how do others compare?" Each hypothesis about alien absence makes us examine some aspect of life or civilization, rare Earth. Then we appreciate how special our planet is, perhaps how lucky we are. Self-destructive aliens. Then we worry about how we too must overcome such tendencies to avoid meeting a similar fate. They're out there but silent. Then perhaps wisdom eventually leads to introspection and peace rather than expansionist noise. Something for us to consider. In the meantime, while we have yet to hear a whisper from another world, we have been sending our own out, in case someone is listening. Beyond the inadvertent TV and radio leakage, we've deliberately sent a few cosmic messages. The Voyager 1 and 2 probes, launched in 1977, and now sailing beyond our solar system, each carry a golden phonograph record filled with sounds and images of Earth. A postcard from humanity, intended for any spacefarer that might find it in the distant future. Those records have greetings in dozens of languages, the sounds of wind and surf, bird songs, music ranging from Bach to Chuck Berry, and pictures encoded in analog form. It's a lovely gesture, optimistic and profound. We sent our story into the cosmic ocean, like casting a bottle with a note into the sea, trusting that somewhere,
someday it might be found. We have also beamed messages at stars, like the binary-coded Arecibo message with basic info about math, DNA, and humanity, and more artistic signals, like a digital message towards a star from a Ukrainian radar telescope containing music and drawings. Will any of these reach an alien consciousness? And if so, when? Perhaps tens of thousands of years from now. These acts are symbolic, a way of saying, we are here, and we want to know you, to the darkness. As our journey in this stage of our cosmic exploration gently fades, it's clear that the question of alien life, whether simple microbes under Martian soil or advanced civilizations across the galaxy, remains open and deeply compelling. We live in a time where we have tools to actually seek answers, and that in itself is something previous generations could only dream of. In the stillness of a night, when you gaze up, you might feel a mix of solitude and connection. Solitude, because the stars seem silent. Connection, because you realize those stars are suns with their own planets, and you, a being made of stardust, are contemplating them.
So, where are the aliens? For now, they remain hypothetical, figments of our scientific predictions and imagination. They might be out there pondering the same question about others, or we might truly be singular, an island of life in a vast, mostly barren sea. Either answer, once finally known, will profoundly shape our understanding of existence. We drift in thought, imagining the many possibilities, our curiosity like a comet's tail glowing in the darkness. The universe doesn't yield its answers quickly, but in our patience and persistence, there is beauty. Perhaps one calm night, centuries hence, our distant descendants will finally pick up a clear melody from the stars, an answer to the question we've long whispered. Until then, we find solace in the search itself, in the unity of humanity, looking outward together, and in the quiet conviction that the mystery is worth pursuing. Each unanswered question is like a star waiting to be discovered. As this stage of our cosmic journey gently fades, we prepare to venture even deeper into those cosmic seas, to explore other profound enigmas that await. The story continues, carried on a tranquil voice through the stillness of space, guiding us further into the unknown. Imagine drifting silently through the depths of space, far from any planet or star. All around you is darkness, a soft and gentle darkness, speckled with the distant light of galaxies. You feel weightless, as though you are a part of the void itself, floating in eternal night. In this tranquil emptiness, it is easy to think that what you see is all that is there. The soft glow of stars and the faint luminous clouds of nebulae. But in truth, the cosmos holds far more than what our eyes can perceive. Beyond the gleam of every star, beyond the reach of our best telescopes, there is something invisible, yet immense. It does not shine or reflect any light. You cannot touch it or hold it in a jar. And yet,
It is all around, woven into the fabric of the universe. This mysterious presence is known simply as dark matter. The name sounds ominous, but dark matter is not dark in the way of shadows or night. It is dark because it hides from us, eluding even our most sensitive instruments. Picture a grand spiral galaxy, much like our own Milky Way, turning slowly in the cosmic night. Its arms sparkle with billions of stars, like a pinwheel sprinkled with diamond dust. At the center, a bright core of light marks a bustling hub of activity. You might think that all the mass of this galaxy comes from the stars, gas, and dust that shine within it. But if you watch how the galaxy spins, a puzzle emerges. The outer stars, far from the center, are moving just as fast as those closer in. It's as if some invisible force is helping to whirl them around, preventing them from drifting off into space. Astronomers first noticed this strange behavior in the motions of galaxies. By all rights, the stars at the edges of a galaxy should be moving more slowly than those near the middle. Much like the outer planets of a solar system orbit the sun more sluggishly than those close in. Yet the stars in the outskirts were zipping along with unexpected speed. It was as though an unseen gravitational hand was gripping them, pulling them around in their orbits with extra strength. This was one of the first clues that a vast amount of mass lurks hidden in each galaxy. Mass that we cannot see. To understand this, imagine a merry-go-round filled with children. If there are not enough kids near the edge, the outer seats might slow down or even fling off anything too loose. But if many children, even invisible ones, are spread throughout, they can hold the ride together, spinning at a steady pace. In galaxies, the stars are like the visible children on this cosmic carousel. Dark matter is like a crowd of invisible riders, adding the necessary gravitational pull to keep the galaxy's rotation steady all the way to its rim. In the quiet darkness of space, dark matter itself makes no sound and no light. It drifts through the cosmos like a ghost, unnoticed, except for the subtle gravity it exerts. You could be surrounded by dark matter right now and never know. In fact, as you drift through our imaginary galaxy, countless unseen particles of dark matter would pass through you every second without a trace. They do not collide with your atoms or cause any harm. They slip through ordinary matter as if it were not even there. How much of this ghostly substance is there? Remarkably, when scientists tally up the matter in the universe, they find that dark matter outweighs all the ordinary matter, the stars, planets, and people, by a large margin. It is as though the bright, beautiful cosmos we see is only the tip of an enormous cosmic iceberg. The vast bulk of that iceberg lies hidden below the surface, invisible but real. If we imagine all the matter that we can see as the foam on the crest of a wave, then dark matter is the deep ocean beneath, supporting the wave and guiding its journey. This realization is both humbling and enchanting. The idea that most of the matter in the universe is unseen makes the cosmos feel a bit like an old, dimly lit mansion filled with hidden rooms and secret corridors. We wander through its faintly illuminated halls, aware that beyond the walls and under the floors, there are spaces we cannot yet enter, mysteries we cannot yet witness directly. Dark matter is one of those hidden structures, a secret framework holding up the visible universe like the unseen beams of a great cathedral. We see the stained glass and the arches, the stars and galaxies, but not the supporting girders in the shadows. For something so pervasive, dark matter remains frustratingly elusive. What could it be made of? Scientists have proposed many ideas. Some say it could consist of exotic particles, different from the atoms that make up everything we are familiar with. These particles might have flooded the universe in the earliest moments after the Big Bang, remaining abundant, yet aloof ever since. Others wonder if dark matter might not be particles at all, but rather massive, dim objects like ancient black holes or failed stars scattered throughout galaxies. Though searches for such things have largely come up empty so far. Consider how we might detect such an invisible substance. It's a bit like trying to find a faint breeze on a still night. You can't see the air itself, but you might notice the swaying of the trees. In space, we cannot see dark matter directly, but we see how its gravity sways the stars and bends the path of light. Yes, even light can be subtly detoured by the gravity of dark matter, much as a pebble creates ripples that divert a stream. When we observe distant galaxies or clusters of galaxies bending light around them in just the way a massive but unseen influence would, it's like seeing the silhouette of something invisible, dark matter, revealing itself by what it does, if not by what it is. Though we have gathered clue after clue of its existence, holding dark matter in our hands, metaphorically speaking, remains one of astronomy's greatest quests. Around the world, deep underground or high on mountain tops, experiments quietly wait for a whisper of dark matter's presence. These detectors are like jars set out on a night of invisible rainfall, hoping to catch a rare drop of this ethereal substance. Every so often, a scientist might excitedly suspect that one of these devices has recorded a faint bump in the night, maybe a dark matter particle brushing past. But so far, each hint has turned out inconclusive, or has vanished with further scrutiny, leaving the mystery intact. Imagine the day when we finally identify what dark matter is. It would be as if a veil had been lifted from our understanding of the cosmos. Suddenly, that invisible scaffolding would come into view, and we could start to paint a fuller picture of the grand cosmic tapestry. But until that day, we continue to search in the dark, guided by curiosity and the faint glimmers of evidence we can gather indirectly. The darkness is not frightening. Instead, it reminds us that there is so much more to learn, and that the universe still holds secrets close to its chest, like a storyteller not ready to reveal the ending of a tale. Even without knowing exactly what it is, dark matter plays a crucial role in the story of the universe. Long ago, in the early universe, matter was spread out almost evenly. Over time, Regions with a little more matter began to draw in more and more through gravity, growing denser. Scientists believe that dark matter, being abundant, started clumping first, forming a sort of cosmic skeleton. Ordinary matter then followed the dark matter's gravity, pooling into these seeds to form galaxies and stars. In a poetic sense, dark matter could be thought of as the dream before the stars were born, an invisible outline, sketch upon which the visible universe was drawn. When you gaze up at the sky on a clear night, you might see the gauzy band of the Milky Way, or perhaps a faint smudge that is the Andromeda Galaxy, our nearest galactic neighbour. As you marvel at their beauty, remember that what you see is only part of the picture. Enveloping each galaxy is an enormous halo of dark matter, extending well beyond the visible edge. These halos are like gently holding hands, cradling the galaxies and keeping their stars bound together. When galaxies come close and interact, or even collide, it is often the dark matter halos that first brush against each other, like giant soap bubbles touching in the vastness of space. Thinking of dark matter invites a sense of wonder. It is a reminder that reality is not limited to what our eyes can capture. There is a richness to the universe that lies in the unseen and the unseeable. How fascinating that the fate of stars and galaxies may be governed by something we can scarcely fathom. It's almost as if the universe has a hidden heart, beating quietly, invisibly, influencing everything we do see. We call it matter, but dark matter could be something more exotic than any matter we know. It does not interact with light, which is why it's dark. It barely interacts with normal matter at all, if ever, aside from gravity's pull. In our everyday world, everything we see around us, from the tiniest grain of sand to the largest planet, is made of atoms, which in turn are made of familiar particles, like protons and electrons. Dark matter, if made of particles, would be something outside this family, a stranger to our world. It might waft through the earth as effortlessly as a breeze through a screen door, rarely hitting anything.
Sometimes, to imagine something truly strange, it helps to draw analogies with things we know. Think of dark matter, perhaps as a kind of cosmic wind. We feel the wind on our skin only when it catches something, a leaf, a sail, or our face. If the air were perfectly still, or if we lacked senses to feel it, we might not know the air itself was there. Yet we would see its effects. Trees swaying, clouds drifting. Similarly, dark matter is like a wind we cannot directly feel or see, but whose presence is betrayed by the dance of galaxies and the choreography of the cosmos. Or perhaps dark matter is like an invisible ink in the book of the universe. The shining stars and galaxies are the written letters we can see under the light, but beneath and around those letters, the invisible ink of dark matter shapes the narrative in ways we cannot directly read. We know the invisible ink is there because parts of the story
wouldn't make sense without it. We just haven't deciphered what it says on its own. The question, what is dark matter, remains one of the great unanswered enigmas in science. It is a question that leads us down a winding path of discovery, through underground laboratories and out to the furthest reaches of space, where galaxies collide and cluster. With each passing year, we learn a bit more. We map the dark matter's distribution across the cosmos, like cartographers charting the coastline of an unseen continent. We crunch data from particle colliders, searching for hints of new physics that might explain dark matter. We refine our theories and build ever more sensitive instruments to listen for that quiet whisper in the dark. Yet, as of now, the answer stays just out of reach. And maybe that's fitting in a way. The universe is in no hurry to give up all its secrets at once. There's a patient, almost gentle pacing to our understanding. We ask a question, we gather clues, and sometimes the answers only raise more questions. Dark matter reminds us to embrace the mystery. In that embrace, we feel the awe of not knowing, balanced by the hope and excitement of one day finding out. In the meantime, even not fully knowing what dark matter is, we can appreciate the beauty of its subtle influence. It helps sculpt galaxies into elegant spirals. It ties galaxies together into immense clusters bound by gravity. It forms a vast cosmic web, with threads and nodes where galaxy clusters reside, like dewdrops on a spider's web glistening in the faint light. And it teaches us humility, a humbling knowledge that the majority of matter in the cosmos is invisible to us, beyond our direct perception, reminding us that our understanding of reality is always evolving. As you continue to drift in your mind through the grand reaches of space, you might feel a quiet companionship with this unseen matter. It has been here since the beginning of time, calmly shaping the destiny of galaxies. Invisible though it is no less real, and its story is intertwined with our own cosmic history. The darkness of space around you is not empty. It is filled with the silent presence of dark matter, cradling the galaxies like precious lanterns afloat in a sea of night. From the mystery of dark matter, our journey moves onward, deeper into the unknown. We have contemplated an invisible substance that fills space. Now we turn to a different kind of darkness. Unlike dark matter, which hides by being transparent and elusive, this next mystery is a darkness born from gravity's overwhelming embrace. It is a place where even light itself cannot escape, where time and space are stretched to their limits. Our voyage of the mind takes us now to one of the most awe-inspiring phenomena in the universe, the realm of the black hole, and the question of what might lie inside these cosmic enigmas. Imagine now that you are gliding toward a black patch of sky, a place where a star once shone but has since vanished. Ahead of you lies a black hole, a true cosmic abyss. At first glance, it looks like nothing at all, just a circular patch of darkness against the starry background. Around its edges, you might see a strange halo of light, perhaps the last rays of shredded stars and heated gas swirling in a bright ring, orbiting the darkness like a brilliant whirlpool around a drain. This halo casts an eerie glow, but the center remains pitch black, a mouth of emptiness in the fabric of space. This is the event horizon, the boundary of the black hole. It's not a solid surface, but rather an invisible threshold. Once anything, whether it's a particle of light, or a spacecraft, or a wandering astronaut, crosses this boundary, it cannot turn back. It is the ultimate one-way door. Outside the event horizon, you could theoretically escape if you had a fast enough rocket. But at the horizon and beyond, gravity's pull is irresistible, dragging everything inward. Even light, which travels faster than anything else in the universe, cannot muster the speed to break free from within that boundary. So the black hole appears truly black, because no light comes out to carry any message of what's inside. What lies inside such a black hole? It's a question that has teased scientists and dreamers alike for decades. If you were to drift past the event horizon, what would you experience? Let's imagine, carefully and calmly, that we could take this plunge. If the black hole we approach is a very large one, perhaps millions of times the mass of our Sun, the journey inwards might initially be surprisingly gentle. You might not even notice when you cross the horizon itself. There is no fanfare, no sudden jolt, just the continued pull of gravity drawing you deeper. The outside universe from which you came begins to fade from view. Light from the stars behind you is bent and reddened until the outside sky above appears squeezed into a dim, circular window, rapidly shrinking. Inside the black hole's horizon, the flow of space and time themselves seems to change. According to Einstein's theory of gravity, space and time are woven together, and a black hole twists that fabric to an extreme. In some ways, moving forward in space inside the horizon becomes as inevitable as moving forward in time. Just as we cannot help but move into the future, anything inside a black hole cannot help but move further inward, toward the center. It's as if the very direction toward the core has become like a trap door in time, every moment carrying you closer and closer, with no chance of stopping or turning around. As you descend, the pull of gravity strengthens. If the black hole is smaller, this would become violent quickly. The difference in gravity between your head and your feet could stretch you out like a piece of taffy, an extreme process whimsically known as spaghettification. But with a gigantic black hole, hundreds of thousands or millions of times the mass of the Sun, the gradient is gentler at first, giving you more time to drift before such effects become overwhelming. Still, no matter the size of the black hole, the end point of your journey would be the same, the central abyss. At the core of a black hole, according to the classical equations of physics, everything that falls in gets crushed to an infinitely tiny point. All the mass, all the information about what fell in, whether it was stars, planets, or light, is thought to be compressed into an unimaginably dense state. We call this the singularity. It's a place, if we can even call it a place,
where our understanding of physics completely breaks down. Densities and gravity become so large that the usual rules no longer make sense, yielding infinities in our calculations. It's like hitting a wall in our theory, a sign that we need new ideas to figure out what's really happening there. So what really happens at or near the center of a black hole? The honest answer is, no one knows for sure. It's one of the greatest mysteries of modern physics. Our current theories give us no clear picture. They just tell us that they themselves fail in such extreme conditions. To truly understand the inside of a black hole, we likely need a new theory, one that blends Einstein's relativity, which describes gravity and the cosmic scale structure of space-time, with quantum mechanics, which describes the very small scale of particles. Scientists have been striving for such a unified theory, sometimes called quantum gravity, which might reveal how nature behaves when gravity is incredibly strong and acting on tiny scales, as it would near a singularity. Without a way to peek inside directly, scientists use their imaginations, guided by math and physics, to speculate. Some have proposed that the core of a black hole might not be a single point at all, but something different. Perhaps a sphere of extremely compressed matter, or a tangled loop of space and time. Others suggest that what we think of as a singularity could even be a bridge to another part of the universe. This is where the idea of wormholes comes in, hypothetical tunnels connecting distant points in space or time. In theory, a black hole could be connected to a white hole somewhere else, a white hole being a bizarre time-reversed version of a black hole from which matter and light can only emerge, never enter. If such things exist, could falling into a black hole somehow spit you out of a white hole elsewhere? It sounds like pure science fiction, and indeed, there's no evidence yet that our universe allows this kind of escape hatch. But the mathematics of Einstein's equations do hint at these exotic possibilities. Another thought some scientists entertain is that perhaps each black hole might be the seed of a new universe in its own right. Imagine that what falls into a black hole gets crunched into a point that then explodes outward on the other side in a kind of new Big Bang, creating a bubble universe separate from our own. This is a speculative idea, of course, but it's a fascinating one. In this scenario, our own universe could even have sprung from the interior of a black hole in a larger parent universe. It's a mind-bending concept. Black holes as cosmic wombs giving birth to new universes. And while it's highly theoretical, it shows just how far our thinking can roam when we consider the depths of these enigmas. All these ideas, wormholes, white holes, baby universes, stem from our attempt to comprehend what our equations are telling us, and from our hope to avoid the dreaded infinities of a singularity. In simpler terms, if our mathematics predict a point of infinite density, perhaps it means we're missing something fundamental, something that would smooth out that infinity into a describable, finite form. Nature might have a more elegant solution than a true physical infinity. But until we have a way to test these ideas, they remain in the realm of theory and imagination. It's important to remember that for anyone who actually falls into a black hole, these nuances might not matter. Their fate
as far as our best understanding goes, is sealed. They will reach whatever is at the center and become part of the black hole's mass. From the outside, observers would never see them actually reach the center. Instead, the falling person would appear to slow down and fade, approaching the event horizon, but never quite seeming to cross it, because the light coming from them gets increasingly red-shifted and delayed. In reality, of course, from the traveller's own perspective, they do cross and continue in. It's as if two perspectives, the outsiders and the insiders, diverge at the horizon, each with its own version of events. This strange difference in perspectives highlights just how peculiar black holes are. They warp not only space and matter, but our very concept of time and reality. Time near a black hole flows differently. The stronger the gravity, the slower time moves when viewed from far away. If you watched a clock fall toward a black hole, you'd see it tick more and more slowly as it neared the horizon. In a sense, the edge of a black hole is not just a where in space, but a when in time. It's like a moment frozen from the perspective of an outside world that will never see beyond that horizon. Listening to these ideas, you might get a sense of just how difficult it is to wrap our minds around a black hole's interior. The language we use, horizon, singularity, wormhole, they're attempts to grasp a reality that doesn't fit our everyday experience. And so we often resort to metaphors. We say a black hole is like a bottomless pit, or like a waterfall in the river of space, that once you go over, there's no coming back. We imagine the singularity as a point of infinite density, a concept that's almost poetry in its mystery, a place where the known laws of nature fold in on themselves like a piece of paper crumpling into a ball. Despite the darkness and the seemingly violent nature of black holes, there is a strange kind of peace in thinking about them from afar, here in the comfort of our imagination, drifting safely at a distance. We can contemplate the paradox of these objects. They are born from death, often the death of massive stars. Yet they might hold the key to new beginnings in ways we don't yet understand. They destroy any object that falls into them, yet in doing so, they might be forging connections to places unseen or even new universes. They are like cosmic yin and yang, representing both an end and, potentially, a beginning. One thing we do know, however, is that black holes are very real. We have observed their influence on the stars around them, even captured images of the glowing rings of material at their edges, highlighting the silhouette of the void. We've heard their collisions through gravitational waves, ripples in space-time that these mighty mergers send across the cosmos. These observations assure us that black holes are not just theoretical oddities. They truly exist out there in the darkness. But such observations mostly reveal the black hole's exterior and its effects. The inside, the heart of the black hole, remains a realm of conjecture, sealed away behind the event horizon's one-way door. For now, the secret of a black hole's interior remains safe behind its horizon. But this isn't the only astonishing thing about black holes. It turns out they are not lone wanderers. In fact, nearly every large galaxy we know, including our own Milky Way, harbours a supermassive black hole at its centre. It's as if the cosmos has placed a heavy, invisible heart in each galaxy's core. Why would that be? What role do these central black holes play in the formation and life of a galaxy? To find out, we must journey from the inside of one black hole to the bustling centers of galaxies themselves, where stars swarm around a hidden giant. Deep in the heart of a galaxy, there is a bustle of stars, swarming like bees around a hive. In our own Milky Way, if you could peer through the thick clouds of dust and gas toward the center, you would see stars moving astonishingly fast, whipping around an unseen object. For a long time, astronomers wondered what could be powerful enough to cause such rapid orbits. The answer became clear. A supermassive black hole, millions of times the mass of our Sun, resides at the Milky Way's core. And it's not just our galaxy. Nearly every large galaxy we observe seems to house one of these cosmic heavyweights in its central regions. Why would a black hole sit at the center of a galaxy? To picture this, imagine a peaceful city park where children are playing. If one child starts running in circles, others might be drawn into the chase. In a galaxy, the black hole's immense gravity is like that lead runner, drawing stars into fast orbits near the center. But the presence of the black hole raises many questions. Did the black hole form first, acting like a seed that helped the galaxy grow around it? Or did the galaxy form first, and over time, matter fell into the center to create the black hole? Perhaps both grew together, each one influencing the other in a cosmic dance billions of years old. In the early universe, long before the Milky Way even took shape, matter was gathering into clumps that would become galaxies. Some regions had more gas and stars forming than others. Those dense regions could have given birth to massive stars, or even triggered direct collapses of gas that, under their own gravity, created black hole seeds. These seeds might have started relatively small, maybe tens or hundreds of times the mass of the Sun. But over time, they would swallow gas and merge with other black holes as smaller protogalaxies joined forces to build larger galaxies. Through this process, a tiny black hole could grow into a supermassive one, just as a small acorn can eventually become a vast oak tree, given enough time and nourishment. On the other hand, it might be that the black hole wasn't strictly necessary to form the galaxy. After all, gravity from ordinary matter and the mysterious dark matter can pull together a galaxy's structure on their own. But once a black hole does form in the center, it can act like a cosmic anchor. Heavy things tend to sink to the center in a gravitational system. Imagine sediments settling at the bottom of a pond. In a newly forming galaxy, any early black holes born from the first stars might gradually sink toward the middle and merge, contributing to a growing central black hole. Over millions of years, this process would concentrate a lot of mass in one small area at the galaxy's core. The black hole at a galaxy's center often remains hidden from direct view, especially if it's quiet and not actively consuming matter. Black holes themselves emit no light, so we infer their presence by how they affect their surroundings. In our Milky Way, for example, astronomers watched individual stars near the galactic center, tracing out rapid, tight orbits. One star, known as S2, was observed swooping in and then swinging far out again on a looping path that repeats every 16 years or so. The only thing that could explain S2's motion was an enormous mass concentrated in a tiny area, far too small to be a cluster of normal stars. This led to the conclusion that a black hole weighing about 4 million suns lurks there, now famously called Sagittarius A. It's awe-inspiring to think about. At the serene center of our swirling galaxy, beyond the busy spiral arms and quiet nebulae, lies a gravitational giant, quietly holding court among the stars. Most of the time, it's relatively calm. Our Milky Way's central black hole is not consuming much material at the moment, so it's dark, and we know it's there only by the motion of nearby stars. But in other galaxies, or perhaps in our own galaxy's past, the central black hole can become a hungry beast. When a lot of gas starts falling into a supermassive black hole, that gas heats up and glows brilliantly before crossing the horizon. The result is a quasar, or an active galactic nucleus, a beacon that can outshine the entire galaxy with the light of accelerated material racing around the black hole. Quasars are among the brightest objects in the universe, visible across billions of light years, and they signal a feast, a black hole devouring matter from its surroundings. Such active phases might be relatively short-lived in the life of a galaxy, but they can have big effects. Imagine our city park again. If one child in the center suddenly starts spinning and kicking up dust, others might be affected. Some might run away from the chaos. Others might be drawn in closer. Similarly, a feeding black hole can send out intense light and even jets of particles shooting out at near light speed from its poles, like cosmic blowtorches. These outbursts can heat up or push away gas in the galaxy. And since gas is the raw material for new stars, this activity could regulate the galaxy's future star formation. In a sense, the black hole can both nourish and limit the growth of its galaxy, providing energy to stir things up, or clearing out its neighborhood and quelling star birth for a time. One of the great mysteries is the relationship we see between the size of a galaxy's central bulge of stars and the mass of its central black hole. It turns out that bigger galaxies, or at least those with big central collections of stars, tend to have bigger black holes. This correlation hints that the growth of a galaxy and the growth of its black hole are closely linked. It's as if every galaxy and its black hole evolved together, like a vine growing around a tree, one shaping itself around the other. How could this happen? Scientists suspect feedback. When galaxies were young and their black holes were actively accreting matter, the energy released, as those quasars and jets, might have blown out excess gas, putting a check on how large the galaxy's starry bulge could grow. In turn, the amount of gas left to feed the black hole would determine how big the black hole could get. Over time, this push and pull could create the balance we observe. The black hole's size and the galaxy's stellar bulge growing in harmony. However, it's important to note that even the largest black hole is usually only a small fraction of its galaxy's total mass. Our Milky Way's black hole, huge as it is just a drop in the bucket compared to all the mass of the stars in the Milky Way. So a black hole is not like a central anchor holding the whole galaxy together. Dark matter and the combined gravity of billions of stars do that job. Instead, the black hole influences primarily the innermost region of the galaxy. It's like the very central gear of a cosmic clockwork, small in size compared to the whole, but intricately tied to the system's history and dynamics. The question, why is there a black hole at the center of every galaxy, invites us to imagine the story of galaxy formation as a grand narrative. Perhaps, in the beginning, there were multiple seeds, small black holes born from the first generation of stars, or direct collapses of massive gas clouds. These seeds found their way to the centers of early galaxies and merged, growing larger as the galaxies themselves merged and grew. The universe, in its infancy, was a crowded place. Galaxies often crashed together, and each time they did, their central black holes likely found each other and eventually coalesced into a bigger black hole amid the chaos of uniting star systems. Over billions of years, through many such unions and continuous feeding on gas, the central black holes swelled to the monstrous sizes we see today. Millions or even billions of solar masses. Yet, why at the center? The center of a galaxy is a natural sink for matter. Gravity pulls everything inward. As a galaxy settles into its structure, its core becomes the busiest crossroads of orbits. If you have a swarm of stars and perhaps a few smaller black holes wandering the galaxy, gravity and dynamics tend to bring the heaviest things toward the middle over time. It's a bit like coins spiraling down those funnel-shaped charity drop boxes. You watch them loop around and around until they inevitably fall into the hole at the center. In galaxies, massive objects drift inward and congregate at the core. So if a black hole exists at all in a galaxy, over time it's likely to migrate toward the center and stay there. In a large galaxy, many such black holes from smaller building block galaxies might have sunk to the center and merged, leaving one grand black hole. There's also the possibility that the central black hole and the galaxy were born almost simultaneously. Some theories propose that in the very early universe, the conditions at the center of a forming galaxy could lead to a direct collapse of a giant primordial cloud of gas into a black hole, skipping the usual step of forming a star first. This would create a massive black hole very quickly, which would then act as a nucleus for the young galaxy, gobbling up surrounding matter and growing while the galaxy around it also takes shape. If this idea holds true, then the presence of a central black hole is almost a byproduct of galaxy formation itself, as inevitable as a whirlpool forming at the drain when water collects. Despite all these ideas, there is still much we don't know. We've only observed a handful of galaxies in enough detail to really measure their central black holes, and even fewer where we can watch how those black holes might be influencing their galaxies. It's like trying to understand a vast forest when we've only examined a few trees up close. We do know that supermassive black holes are out there in nearly every large galaxy we check. Not having one is the exception, not the rule. Though some small galaxies might lack a supermassive black hole, perhaps because they haven't had the chance to grow one yet, or their history was different. Thinking about a galaxy with its central black hole can evoke a poetic image. A whirling spiral of stars with a tiny dark gem at its core. That gem is invisible, yet its presence is felt by the stars that race around it. It's almost like each galaxy has a secret. At its center lies a dark heart, one that we can't see directly, but that has profoundly influenced the galaxy's life story. This dark heart doesn't beat like ours, but occasionally it roars. When it feeds on infalling gas or stars, it can blaze with energy. And when it's quiet, it sits in stillness, a reminder of past feasts and future possibilities. The mystery of why galaxies have central black holes is also a reminder of the interconnectedness of cosmic phenomena. We started by thinking of black holes as exotic, isolated things, but here we see them as an integral part of how galaxies themselves evolve. It's a beautiful example of nature's tapestry. Pull on one thread, the black hole, and you find it's connected to the whole design, the galaxy's structure and history. The exact reasons and mechanisms behind this connection are still being explored, but the outline of the story is coming into focus bit by bit. For now, we can imagine that every galaxy drifting through the universe carries with it an ancient companion in its core, a supermassive black hole that has been there for eons. In our mind's eye, if we drift across the cosmos and visit galaxy after galaxy, we'd find each one with a unique central black hole, like finding a different jewel in the heart of each cosmic city. Some shine brightly with furious energy, others slumber quietly. Some might be relatively small, others among the largest black holes we can conceive. But in almost every case, there the black hole sits, hidden in the glare of its surrounding stars, a testament to a universal theme in cosmic evolution. As our journey takes us through these galactic centers, we cannot help but be amazed at how the universe organizes itself. From invisible dark matter sculpting cosmic structures to black holes anchoring galactic hearts, we see that even in chaos there is order, patterns that repeat across billions of light years, and underlying everything, guiding the dance of galaxies, stars, and black holes, is the flow of time. With each orbit of a star around a galactic center, millions of years pass. Black holes grow over eons. The universe itself has a timeline, from the fiery birth of the Big Bang to the star-filled cosmos we see now. Which brings us to perhaps the most profound mystery of all, the nature of time itself. We experience time every moment of our lives. It's so familiar. Yet when we try to pin down what time truly is, it slips through our fingers. We've journeyed through questions about matter and space, and now our path leads to a question that touches everything we know. Does time exist? Or is time just an illusion, a convenient way to track change? In the vast stillness of space, As we watch galaxies spin and stars burn through their fuel, time seems to be the quiet rhythm to which all of creation moves. But is it a drumbeat set by the universe, or is it set by our own perception? With a gentle sense of wonder, we turn to consider the enigma of time. Time. We live by it. We measure it. We feel it passing in every heartbeat. Yet, when we pause and try to grasp what time really is, it becomes elusive. Think of moments in your life, the warmth of a childhood summer day that seemed to last forever, or a happy gathering that flew by in an instant. Time can stretch and compress in our perception, but beyond how we experience it, a deeper question lingers in the quiet of the mind. Is time truly a fundamental part of reality, or is it something we humans have conjured to make sense of change? Imagine the universe at large, far from the ticking clocks and calendars that rule our daily lives. In the silent expanse of space, a star explodes in a distant galaxy, while elsewhere, a planet coalesces from cosmic dust. Events unfold, one after another. We use the word time to sequence these happenings, to say that one event occurs before or after another. But is time itself flowing, like a river carrying events in its current? Or are events simply happening, with time being our way of mapping them? This is a puzzle that philosophers and scientists alike have pondered for ages. We often picture time as an arrow, moving relentlessly forward. In our experience, we remember the past, but cannot revisit it. We look toward the future, but cannot jump ahead to see it. There's a clear direction: yesterday, today, tomorrow. This arrow of time feels fundamental. Yet, the laws of physics, interestingly enough, don't pick a preferred direction. The equations that govern how planets orbit or how particles move can typically run forward or backward in time and still make sense. If you were to watch a film of two planets circling each other, the physics would hold true, whether you played it normally or in reverse. So why, in reality, do we see time march forward and never backward? One clue lies in something very simple. Imagine a cup of hot tea set on a table. After a while, the tea cools down as heat flows from the hot liquid into the cooler air of the room. Left alone, the hot tea will always transfer heat to its surroundings, eventually reaching the same temperature as the room. The reverse, a cold cup of tea spontaneously heating up by absorbing warmth from the room, never happens. This is one aspect of the second law of thermodynamics. Systems tend to go from order to disorder, from concentrated energy to spread out energy. In a word, entropy, a measure of disorder, increases with time. This gives a direction to events. Heat flows from hot to cold, not the other way around. That gradual increase of entropy provides a kind of arrow for time in our macroscopic world. We remember the past because it was a state of lower entropy. The tea was hot and the room cooler, a more ordered difference. As time goes on, things mix and settle. The heat disperses, making the combined system more uniform and disordered. In the far future, the universe might reach a state of maximum entropy, where everything is spread out and nothing noticeably changes. In such a state, time would lose much of its meaning, because change, which is how we perceive time, would cease. But is this arrow of increasing entropy what time is? Or is it just one aspect of time's behavior? Some scientists suggest that time might emerge from something more fundamental, perhaps from the quantum world, or from the structure of space-time at a deep level. Others argue that time is as real as space, just another dimension that we happen to experience in one direction. In Einstein's theory of relativity, time and space are intertwined into a single fabric called space-time. There isn't a universal, absolute time that ticks the same for everyone, everywhere. Instead, how fast time passes can depend on your motion or the gravity you're exposed to. Time for an astronaut aboard the International Space Station runs a tiny bit slower relative to people on the ground because of the combined effects of speed and Earth's gravity. This has been measured with precise clocks. Time near a massive object, say a black hole or even the Earth, moves a bit more slowly compared to time far away in weaker gravity. These are not just thought experiments, they're observed realities. GPS satellites, for instance, have to account for slight time differences due to their speed and altitude, otherwise their positioning data would drift. So, time exists in relativity, but it's not a one-size-fits-all flow. It's flexible and personal, woven together with space. If time can stretch and bend, we might wonder, could it be that time is simply a measure of change? Think of a simple scene, a sunbeam moving across a room as the afternoon passes. We often say the sunbeam moves as time goes by. But another way to think of it is, the sunbeam moves, and we use time to measure its changing position. In other words, the change is fundamental, and time is the concept we use to quantify that change. Some theorists have proposed exactly this, that instead of time driving the universe's evolution, it's the evolution that gives rise to the sense of time. Consider our memories. We remember things in sequence. Morning comes, then afternoon, then night. This gives us a strong impression that time is flowing. But here's a thought experiment. Imagine the universe in a single frozen instant. Nothing moves, nothing changes. Would time exist in that frozen snapshot? Most would say that without change, time has no meaning. If absolutely nothing happened, if no clocks ticked and no hearts beat, there would be no passage of time to mark. In that sense, time could be seen as an emergent property of the changing universe. As soon as things can happen and change, we have a notion of before and after, and thus we have time. Another profound idea comes from considering the entire history of the universe at once. Some scientists and philosophers talk about the block universe concept. In this view, past, present, and future all coexist in a four-dimensional space-time, the way every location in a landscape exists all at once. We, as conscious beings, move through this landscape along the time dimension, experiencing only one moment at a time, as now. Imagine time as a grand book, with each page representing the state of the universe at a given moment. We live reading the book page by page, unaware of the next page until we turn to it, and unable to flip back to previous pages, except in memory. But the book in its entirety, past, present, future, exists as a whole. If this is a correct picture, and it's an interpretation of relativity that many hold, then in some sense, every moment that has ever happened or will happen is still there, just not accessible to us once our journey has carried us beyond it. This idea challenges our intuitive sense of now being special, but it arises naturally from the mathematics of relativity, which don't single out a present moment as unique. Then there's the question of the beginning of time. Did time itself have a starting point? According to the Big Bang theory, our universe, and time as we know it, began around 13.8 billion years ago. Asking what happened before the Big Bang is tricky, because if time began with the Big Bang, there may not be a before for anything to happen in. It's somewhat like asking, what's north of the North Pole? The concept of north stops at the pole. Similarly, it might be that time started ticking with the birth of the universe, and talk of before is meaningless. Of course, these are edges of our understanding. Some theories, like certain models of quantum cosmology, imagine that our Big Bang might have been one phase in a larger cycle, or that time existed before, but in a different form. We simply don't know yet. But it's mind-boggling to think that time itself might have come into being, that there might have been a first moment. Some cutting-edge physics theories imply that on the tiniest scales, the flow of time might not be what we think it is. In the realm of quantum gravity, a not yet fully realized theory that would merge quantum mechanics with general relativity, time might not even be a fundamental ingredient. Certain approaches, like loop quantum gravity, suggest that space, and perhaps time, are made of discrete bits, and time might emerge from more basic, timeless laws. Much like temperature emerges from the motion of particles, even though no single particle has a temperature by itself. Imagine zooming in so far on the fabric of reality that time becomes fuzzy or fragmented, and cause and effect lose their clear order. It's very speculative, but it shows that even the concept of time could be subject to deeper principles that we're only beginning to guess at. All this can sound very abstract, but it circles back to our everyday experience in a beautiful way. Whether or not time is an illusion or a fundamental dimension, we exist in a universe where we experience it. Time is woven into our language and biology. We age, we have natural rhythms, we recall the past and anticipate the future. Even if ultimately time turned out to be an emergent concept, it's an incredibly consistent and useful one. We set our lives to it, like musicians following a cosmic metronome. Perhaps the question, does time exist, has two layers of answer. Yes, time exists, in that it's an inseparable part of how the universe works,
and how we live within it. But perhaps not in the way we think, since our intuitive picture of time might not capture its true essence. It might be helpful to think of an analogy. Consider the color blue. Blue certainly exists as a perception. We see the sky and say it's blue. But in physical terms, color is a certain wavelength of light interpreted by our eyes and brain. If there were no beings to see it, those wavelengths would still bounce around. But the concept of blue, as we know it, would be moot. In a similar way, time could be like the color of change. Change happens, and our minds paint a picture of time to make sense of it. Without minds or change, maybe time as we know it wouldn't exist, even though the potential for it might be built into the universe. Think of sitting on a quiet beach, watching waves roll in. You hear the rhythmic crashing of water, one wave after another. That rhythm is like time, giving a tempo to the experience. Now imagine the ocean, with no one there to watch or listen. Waves would still rise and fall, events would happen, but the concept of a rhythm or a timing between waves requires someone to perceive it. In reality, the rhythm is inherent in the waves themselves, but recognizing it as rhythm is something a mind does. Time might be similar. Events contain their own rhythm, and time is our way of noticing and measuring that rhythm. Our minds also contribute to the sense of time's flow. We string moments together into narratives. As you lie in bed drifting to sleep, perhaps even now as you listen, your thoughts meander. You might recall a memory, then let it go and sink into a dream, and then that too fades. There is a gentle, one-way drift in our mental experience. We can't typically jump back to a previous thought, as if rewinding a recording. We flow onward. This psychological time is intimately familiar. It's essentially what our conscious life is. And yet, we all know it's subjective. An hour engrossed in a delightful activity can feel like a minute, while 5 minutes waiting in anxiety can feel like forever. This personal, elastic sense of time hints that time isn't as uniform as the ticking of a clock would suggest. It has an internal dimension that is tied to our experience. So, does time exist independently out there, or is it part of the story we tell ourselves? It might be both. Time exists as part of the universe's structure, since we can measure it and predict things with it reliably in physics. Yet it might not exist as a standalone thing separate from the events and changes that happen. If all events ceased, would time still flow? It's a bit like asking if a clock still ticks when no one is around to hear it. The clock does move, yes, but the concept of ticking lives in a mind that notices the sound. Remove all matter, energy, and change from the universe, and time becomes a lot like an empty concept. Nothing to mark it, nothing to distinguish one moment from the next. One way or another, time is deeply tied to existence. If space is like the canvas of the cosmos, time is the dimension that allows the painting on that canvas to develop. It allows things to happen, to develop, to age. It's why stars have life cycles, why galaxies evolve, and why we have personal histories. Even if someday we discover that time is an emergent phenomenon
rather than a fundamental one. It remains the medium through which the story of the universe plays out. Another lingering mystery about time is why we can only move in one direction through it. In space, we can turn around and go backward. In time, we seem stuck going one way. Time travel into the past remains purely speculative and, many argue, impossible due to paradoxes it could create, like the famous grandfather paradox. Perhaps the one-way flow is simply a fact of our universe, tied to that entropy increase we discussed. Or maybe there's something deeper that prevents backward travel, something built into the fabric of reality to protect causality, the principle that causes come before effects. In any case, as far as we know practically, we ride time's arrow forward and forward only, which gives life its bittersweet quality. Moments once gone become memories and cannot be revisited except in our mind. In daily life, we treat time as a precious resource. We talk about saving time, wasting time, making time for something. We celebrate birthdays to mark the passage of years. We commemorate anniversaries. We reflect at the end of each year on how time has flown. Perhaps part of why time fascinates us is because it is intertwined with our sense of mortality and change. It is the dimension of inevitable change. Without time, everything would be frozen, but with time, everything is in flux. We find that beautiful when it brings growth and new experiences, and sad when it means loss or the end of something cherished. As we come to a gentle pause in our cosmic journey, let's reflect on this mystery of time. It accompanies us in every step of our exploration. We started by delving into hidden matter, then ventured into black holes and galaxies. And all along, time was the silent backdrop of each scene. Whether time is an illusion or a fundamental thread in the universe's fabric, it remains one of the most profound enigmas. Every tick of a clock, every dawn and dusk, every heartbeat reminds us that we are moving through something we call time, even if we don't fully grasp its true essence. The enigma of time invites us to be comfortable with not having all the answers. It echoes a theme that has followed us on this journey. The universe is full of secrets, and part of its magic lies in that very mystery. Perhaps in the future, scientific discoveries will shine more light on time's true nature, or perhaps time will always retain some of its secrets, giving us endless material for wonder and contemplation. Either way, we can savor the experience of time, the flowing present that carries us from one moment to the next. For now, simply feel the moment you're in, the present. This ever-moving, ever-changing now is something we share with the cosmos. Stars are being born and dying in this very moment. Galaxies are colliding in slow motion. And somewhere out there, a civilization might be looking up at their sky and pondering time just as we are. We are all riders on this grand river of time, together. Our journey thus far has carried us across the universe and deep into cosmic mysteries. Each question we explored
opened into another, like an endless vista of stars beyond stars. Though we pause here for now, the voyage is far from over. The universe still brims with unanswered questions and wonders yet to be discovered. In the quiet darkness, we drift gently onward, carrying with us the awe of what we've seen and the anticipation of what lies ahead, as the story of the cosmos continues to unfold. In the silent theatre of the night, beneath a canopy of countless stars, the cosmos whispers its ancient secrets. The darkness above is vast and serene, dotted with gentle lights that have travelled for eons to reach our eyes. As we lie back and gaze upward, feeling the stillness of the night, it's almost impossible to imagine that this peaceful sky is actually alive with motion. Yet, beyond our sight, the entire universe is stretching and growing like a vast cosmic ocean, steadily swelling, tide by tide. For generations, people looked at the stars and thought the heavens were timeless and unchanging, a silent, eternal tapestry of lights. But about a century ago, we began to learn something astonishing. The universe itself is expanding. In the 1920s, astronomers like Edwin Hubble peered through their telescopes at faint, distant nebulae and discovered they were not just clouds of gas nearby, but other galaxies far beyond our own. More surprising, those galaxies were moving away from us. Their light was stretched to redder colours, a sign that they were racing into the distance. It was as though space itself were carrying them off, expanding in all directions. This revelation transformed our view of the cosmos. The universe was not a static stage. It was dynamic, changing, growing. One way to imagine this expansion is to picture a giant balloon with small dots drawn on it. The dots represent galaxies, and we live on one of those dots. Now imagine the balloon being slowly inflated. As it expands, each dot moves away from every other dot. To any given dot, all the others seem to be drifting farther apart. Likewise, in our universe, as space expands, galaxies are carried apart from one another. Importantly, it's not that galaxies are flying through space away from each other like shrapnel from an explosion. Rather, space itself is stretching between them. If you could see the universe on the largest scales, you'd see distances growing like taffy being pulled. Early on, scientists reasoned that if the universe started with a big bang and everything has been rushing outward since, then over time, the pull of gravity from all the matter might slow that expansion down. Perhaps eons from now, the expansion might even stop or reverse if gravity had its way. For much of the 20th century, astronomers tried to measure if the expansion was slowing. Many thought the cosmos might eventually stop expanding and maybe collapse in a big crunch in the far future, or at least coast along at a steady size. It was a reasonable guess. After all, gravity pulls on everything, and what goes up should eventually slow down. Then came a remarkable discovery, a quiet revolution in our understanding. In the late 1990s, two teams of astronomers were observing distant exploding stars, stellar beacons known as supernovae, to gauge the universe's expansion over time. These supernovae are like mileposts,
extremely bright and visible across vast distances, allowing us to measure how fast their host galaxies are receding. The expectation was to see that those far-off galaxies were receding a bit more slowly than nearer ones, indicating that gravity had been tugging on them over billions of years and gradually slowing the expansion. But to everyone's surprise, they found the opposite. The distant galaxies weren't slowing down at all. They were actually moving away faster and faster. The expansion of the universe was not decelerating, it was accelerating. This was a completely unexpected twist. Overnight, our view of the cosmos changed from a firework that might eventually fizzle out to an ever-accelerating rush into the unknown. It was as if the universe had, against all odds, hit the gas pedal. To explain this, scientists proposed that some mysterious force or energy must be at work, something pushing everything apart, counteracting gravity on the largest scales. They gave this elusive influence a name: dark energy. The name sounds ominous, but it's not meant to be scary. Dark simply signifies that we don't yet know what it is, and energy implies it's something intrinsic to space, driving things apart. So, why is the universe expanding so fast? What is this strange dark energy speeding up the cosmic growth? The honest answer is, we don't know for sure, but we can describe what it's doing. Imagine an invisible, gentle pressure woven into the very fabric of the universe, something like a cosmic breeze that we cannot feel directly, but that steadily pushes galaxies apart. Or think of it as a kind of anti-gravity, a subtle effect that instead of pulling things together, as normal gravity does, urges the vast reaches of empty space to expand. Whatever it is, this mysterious energy seems to make up nearly 70% of the cosmos, if our measurements are right. In other words, most of what's out there is this unseen influence stretching space. We don't notice this expansion here in our daily lives. Planets, stars, even entire galaxies are held together tightly by their own gravity and aren't being torn apart by the stretching of space. The distances on those scales are just too small for dark energy's effect to show. It's only over truly enormous expanses, millions of light years between galaxy clusters, that this repulsive push becomes significant. You can imagine that our local cosmic neighborhood, our solar system, our galaxy, is like a tight-knit family bound by gravity's love, while dark energy is a faint tug trying to pull the family members apart. But that tug is far too weak to overcome their bonds. Only out in the sparsely populated intergalactic wilderness does dark energy's influence fully reveal itself. The result of this influence over billions of years is breathtaking. Not only are galaxies moving apart, but the speed at which they separate increases over time. What does this mean for the distant future? If this accelerating expansion continues unchecked, it paints a melancholy yet majestic picture of the cosmos in epochs to come. Galaxies will drift farther and farther from each other. Those that aren't gravitationally bound to us will gradually slip away beyond the horizon of what we can see. The night sky, which for us is adorned with the light of countless galaxies visible in our telescopes, will become darker and emptier for observers in the far future. Millions, then billions, then trillions of years from now, distant galaxies will fade out of sight one by one, like lanterns being carried off into an endless night. Interestingly, we find ourselves living at a very special cosmic time. Right now, in this era of the universe, the sky still holds the glow of myriad galaxies. We can study them, marvel at them, and piece together the story of how our universe has grown. But imagine an epoch so far ahead that it almost feels abstract. Trillions upon trillions of years from now, when the expansion has carried all other galaxies so far away that their light no longer reaches us. In that far-off age, the cosmos would look vastly different. Future astronomers, if any beings are around then, might gaze into the sky and see nothing beyond our local cluster of stars. They might not realize that a grand universe ever existed outside their galactic island. They would live in what, for them, would be an island universe, essentially marooned with their own galaxy, the rest of existence receding out of reach, its former brilliance hidden beyond an unbridgeable gulf. The thought that we live in a time when we can witness the larger universe is, in a way, a gift. Today, as we ponder why the cosmos is expanding so fast, we have evidence all around us of that expansion. We see galaxies in every direction rushing away. We detect a faint afterglow that fills all of space, the cosmic microwave background, which is like a memory of the universe when it was young, now cooled and stretched to gentle microwaves after billions of years of expansion. These clues are available to us now, like pages from a history book still open for us to read. In a far future of lonely galaxies, those pages would be sealed blank, the clues gone, or impossible to interpret. So, as strange as it sounds, we are fortunate to exist at a time when the universe still reveals its true nature to us, allowing us to learn about its expansion firsthand. All of this knowledge fills us with both wonder and humility. Here on our tiny planet, we've discovered that we are part of a universe that is not static, but alive with motion and change. The fact that space itself can stretch, carrying galaxies with it, stretches our imagination as well. It reminds us that the cosmos is dynamic and full of surprises, that there are forces at play we never knew about until we looked carefully at those distant stellar beacons. As we lie under the quiet sky, thinking about this speeding expansion, there is a peaceful feeling in knowing that for all the immense drama playing out across galaxies, here and now, we are safe on our little world. The expansion of the universe won't tear apart our home or our galaxy for countless eons, if ever. Our night sky will continue to sparkle with familiar stars for a very, very long time. In our lifetimes, and for many generations to come, the changes in the cosmos will be imperceptibly slow. The universe may be rushing outward on a grand scale, but on the human scale, it still appears calm and constant. contemplating why the universe is expanding so fast, ultimately leads us to even deeper questions. To truly understand this cosmic acceleration, we might need to know how the universe began and what set everything in motion. It makes us wonder, how did all of this start in the first place? What was the universe like at its very dawn? And what, if anything, came before? These questions beckon us further back, to the threshold of time itself, as we continue our gentle journey through the cosmos. Since ancient times, under skies just like tonight's, people have wondered how the world and the stars above began. Every culture crafted stories about the dawn of the universe, tales of cosmic eggs, or gods, or serpents, striving to explain how everything could emerge from nothing. Today, we approach this profound question with scientific curiosity, but the wonder behind it remains the same. We still gaze upward and ask, how did it all start? And if the universe had a beginning at the Big Bang, what, if anything, was there before? To imagine the very beginning of time, let's journey back as far as our understanding will allow. Picture rewinding the cosmic story, going back further and further into the past. We pass the long sweep of cosmic history in reverse. Galaxies drawing closer, stars unforming into gas and dust, the universe contracting, heating, brightening as we push back toward its infancy. Eventually, we reach a point around 13.8 billion years ago, when everything we know, every bit of matter, every ray of light, even space and time itself, was concentrated into a state of almost unimaginable density and heat. This is the moment we call the Big Bang, the beginning of our universe, as far as we can tell. It wasn't a bang, like an explosion in space. It was more like the sudden appearance of space and time, an energetic unfolding of reality from an initial seed. Now we face a question that makes our minds spin in the quiet of the night. What came before the Big Bang? It feels natural to ask, because in our everyday experience, every event has something that came before. Every day has a yesterday. Every story has a prologue. But when we talk about the origin of the universe, we find our usual ideas of cause and effect start to break down. We're peering over the edge of the known, into a realm where our intuition might not guide us anymore. It's as if we stand at the shore of a great cosmic ocean, looking out into a dense fog and wondering if there are lands beyond, lands we cannot see and aren't even sure exist. One possibility is that the question, what came before, might not have an answer that makes sense to us. If time itself began with the Big Bang, then asking what came before it is a bit like asking what lies north of the North Pole. There is no north beyond the pole. That direction just ceases to exist. Likewise, if time truly began when our universe began, there may simply be no before for us to find. The Big Bang would be the starting point of time, the first tick of the cosmic clock. In that case, the concept of before the Big Bang might be as meaningless as the idea of a time earlier than time itself. This idea can be very hard to wrap our heads around. We, who live every moment immersed in time, can hardly imagine time not existing at all. Try for a moment to picture absolute nothingness. No people, no stars, no space, and hardest of all, no time passing. It's nearly impossible. Our minds inevitably picture something, perhaps a vast, empty darkness. But even darkness is something. It has a sense of space and duration. The absence of time and space altogether is not something we can truly envision. So if the Big Bang was the beginning of time, it means the universe's story begins with chapter 1, and there was no prologue before it. A truly hard concept to grasp, yet oddly poetic in its own way. Human curiosity, however, doesn't stop just because a question is difficult. Over the years, scientists and thinkers have devised inventive theories to explore what might have preceded the Big Bang, if anything. One idea is that the Big Bang wasn't a unique, one-time event, but part of a much larger, possibly infinite, cycle. In this scenario, the universe could go through endless epochs of birth, growth, and death, expanding, then contracting, over and over, like a cosmic heartbeat. Perhaps our universe is just the latest expansion phase. Maybe long ago, before our Big Bang, there was another universe that had expanded and then collapsed in on itself in a big crunch. From that dense state, perhaps a rebound occurred, a new Big Bang, giving birth to our cosmos. In such a cyclic universe, the answer to what came before the Big Bang would be another universe, another cosmic cycle. Time would be like a circle rather than a line. There would be no beginning or final end, just an eternal series of universes breathing in and out, each Big Bang a kind of cosmic dawn following a preceding dusk. Another idea is that our Big Bang might have been a random, spontaneous event in a larger reality, perhaps one where nothing isn't truly nothing. Some scientists speculate that before our universe, there might have existed a sort of quantum vacuum, a state empty of matter and energy as we know them, but still teeming with potential, governed by the strange rules of quantum physics. In that nothingness, things can happen without a clear cause, because even emptiness has a kind of jittery energy at the smallest scales. Perhaps a fluctuation in that primordial vacuum energy caused a tiny bubble to form, a little speck of space-time that suddenly began to expand. That was our Big Bang. You might picture it like an ultra-quiet, dark sea, where occasionally a bubble of foam appears and grows. That bubble being our entire universe, swelling from microscopic to vast. Or imagine an endless night where, out of nowhere, a spark of light flares into being, small at first, then spreading out to become everything. In this view, the Big Bang was a transition from a quantum nothingness, which is not truly nothing, to the something of our expanding universe. Yet another concept comes from a proposal known as the no-boundary idea, associated with physicist Stephen Hawking, among others. According to this idea, asking what came before the Big Bang is like asking what's south of the South Pole. It simply isn't applicable. They suggest that as we trace time backwards toward the Big Bang, time might sort of soften or behave in a less time-like way, a bit as lines of longitude do as they approach the pole. At Earth's south pole, all the lines of longitude meet. There is no further south beyond that point. Similarly, the no-boundary proposal imagines the universe as being finite in time, but without a distinct beginning. Time could be thought of as a dimension that, at the very start, was curved in such a way that one could travel back in time only to a boundary that is smooth, not a hard edge or singularity. In simpler terms, the Big Bang might not have been a traditional explosion from a pinpoint, but rather a kind of rounded-off beginning, the universe transitioning from an earlier state where time was perhaps more like a direction in space. In that case, talking about before the Big Bang might be as meaningless as talking about going further south than the South Pole.
All these ideas are attempts to illuminate what is, at least for now, hidden behind a veil.